Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're done with talking about the formation of stars and protostars, and now we're going to actually see how low-mass stars like the Sun evolve with time. And stars themselves change with respect to the course of their histories and how they actually evolve as they use up their fuel from the moment they are born. So let's look at exactly how that's done. But the thing we got to remember is that most of the all the stars in the sky are really quite boring. Most of the stars are insanely boring because less than half the mass of the Sun. They do some really boring stuff that we'll look at the end. It only takes one slide to explain it. So 85% of all the stars in the entire Milky Way can be explained with one slide after we're done talking about the Sun. But we're going to then go back and later things, look at the really more dramatic things, such as massive stars that populate the cosmos with heavier elements. But what we'll talk about this time is how a star like the Sun changes with time. And so once again, let's start over with the life cycles of stars. This comes from the Chandra group, and we see that the mass goes from the low mass stars from the bottom of this graph and the high mass stars from the top of this graph. And as time progresses from left to right, we see that there's different flavors of protostars. The more massive the protostar, they do something slightly different. And so we're going to be talking about the bottom three tiers, which are the brown dwarfs, which don't really serve much of a purpose. So we're just going to say right now what happens to a brown dwarf. It's less than 8% of the mass of the Sun, or 0.08 solar masses. It does not initiate fusion in its core. It just simply contracts like a protostar under gravitational pressure, and that releases heat, and it does that for a very long time. And it becomes a brown dwarf, and forever it is a brown dwarf. It does nothing. But we will talk about red dwarfs, which then eventually become white dwarfs. But we're going to look at the third tier, which is a Sun-like star that starts from a protostar, becomes the Sun-like thing, becomes a red giant, forms this thing called a planetary nebula, and a white dwarf. And we'll talk about some of the other stuff later, but the top bunch we will talk about next time. So the life cycles of stars tell us how stars are born, how they live, and how they die. So the source of the life of a star is hydrogen fusion in its core. Every star that you see in the night sky, every single one of them is fusing hydrogen into helium in its core at least. Some of the other brighter stars, such as Betelgeuse or Bellatrix, might be fusing helium in their cores. But our real question today is, what happens when hydrogen is done, when after helium is created? Well, for stars like the Sun, right now the core is too cool to ignite helium fusion. It's just not hot enough. And therefore, an inert helium core is slowly building up in the center of the Sun. For the Sun, the main sequence lifespan, which is the same thing as saying it's burning hydrogen, we say burning, but mostly we mean fusion, so I'll loosely conflate the word burning with fusing. So hydrogen fusion or hydrogen burning, the lifetime, is the main sequence of a star. And the Sun will go about 10 billion years if it's about one solar mass. That's what that M sub target means. That means one solar mass. But if it's a tenth of mass of the Sun, then it can live up to 10 trillion years, or 10 to the 12th, or 10 to the 13th years. It can live a long time, and these are the red dwarfs. They're really incredibly boring, incredibly dim, but they're the most common star of all. So the evolutionary cycle of the Sun kind of goes with that peculiar graphic across the top. For about 10 or 11 billion years, the Sun is a mean sequence star. Then for about 1.25 billion years, it's a red giant. Then it becomes what we'll talk about, a horizontal giant branch star for about 100,000 years, an asymptotic giant branch for about 20 million years. It'll pulse itself apart over 500,000 years, and it will become a planetary nebula for only about 10,000 years. And at the end of its lifespan, it will be a white dwarf, about half the mass that it started off being. Right now, the Sun is about 4.5 billion years into its life of approximately 11 billion or 11.5 billion years, and that's what we're going to talk about. So in the center of the Sun right now, there's hydrogen core burning, and it's fusing hydrogen into helium, and the process is predominantly the proton-proton chain, and that's what it is roughly at 15 million Kelvin, which is in the core. If it was a little hotter, maybe about 18 million Kelvin, then the Sun would be burning through the CNO cycle. but right now it is currently using the carbon, nitrogen, oxygen cycle. I think we talked about that before, but we'll talk about it again later in later talk. So right now it's going to be doing this for about 11 billion years. And the structure of the sun is as an inert helium core down in the core. It just kind of sinks to the center. That's not participating in anything, and all of the core is completely composed of helium. Surrounding it is a hydrogen-burning core, and surrounding that is the radiative zone, which is kind of reddish there, and then the convective zone, which would be yellow, that we see today, which is the granules and supergranules in the sun, as well as all the active regions on the surface of the sun. But when it starts to run out, that's what we call leaving the main sequence. Because on the main sequence, there are two things that are always in balance. One, there's a gravitational pull that's pulling the star together, and it's balanced by the outward pressure because of the heat from the center. So if it heats up a little bit, so we got to remember the balance now. If it heats up a little bit, the star will expand. And once it's expanded, then it'll cool down in the core. And when it cools off in the core, then it'll start contracting again. And so therefore, this is kind of a normal balance. And once it contracts too much, it'll heat up too much and it'll expand again, just like a normal gas. This is a balance in equilibrium. So a thermal balance and a hydrostatic equilibrium and a thermal equilibrium. So when it leaves the main sequence, the appearance of the star changes. I'm not going to go through all of this to the important things, but basically the temperature rises in the core, the temperature rises on the surface, or at least cools on the surface, then radically rises. We'll see why that is. The diameter of the sun radically changes and gets extraordinarily large, and the central temperature steadily climbs, even though the surface temperature steadily drops, which is interesting. And each successive stage is shorter and shorter and shorter in the sun's life. So how does the sun evolve? So what we do is that researchers using computer codes create models using those equations that I showed you in a previous lecture for stellar interiors and for the equations of hydrostatic equilibrium and the equations of stellar structure. All of those things can be plugged into computer codes, and you look at the exterior of the sun, the mass of the sun, the luminosity of the sun, the composition of the sun as we see it on the surface, and then we run it backwards in time into the center of the sun in order to get the central conditions. And that is called a computer model. So all of the computer models that give us the numbers of the star, then we can make a map of the inside of the star and see how changes in the core of the star affect the changes on the surface of the star. And so here are a couple of recent articles. They're not that recent, but there's been many others. But these are some typical models that can be done. And let's start it off. So we talked last time about the nature of protostars. And the sun took about 50 million years to form from a big molecular cloud. And that core, such as like Barnard 68 or other kinds of large molecular clouds, took about 15 million years to collapse down into a star. It reached the main sequence about 4.5 billion, and we're going to use MYR, meaning million years, and GYR, meaning gigayears. So MYR means 10 to the 6th years, and GYR means 10 to the 9th years. So those are our abbreviations for today. And when the sun first dropped onto the main sequence, where it has been since we would call its birth, we call that the zero age mean sequence, when full hydrogen initiation occurred, and there was thermal equilibrium as well as hydrostatic equilibrium. Once all those three things were satisfied, then the star can be called a zero age main sequence star. Now, at that time, the sun was a bit fainter. It was only about 70% the current luminosity that it is today. It was also a little bit smaller, about 90% of its current radius, and it was actually a little cooler. It was under about a few hundred degrees Kelvin cooler, 200 Kelvin cooler at its surface than we see today. So that's the zero-age main sequence for a single solar mass star. And so I'm going to, again, we're going to plot the evolution of the sun on an HR diagram. So we have, of course, on the left-hand side, the luminosity of it, as well as the temperature, so just like our standard HR diagram. Now, the sun today About 4.5 billion, or giga-years later, 4.55 times 10 to the 9th years later. Actually, it's well understood that the sun is about 4.567 billion years old, so we'll stick with that. The current mass is about 2 times 10 to the 30th kilograms, and that's what it's going to stay until it's dead, until it starts doing the throes of old age, when it actually will lose a significant amount of mass. The current radius of the sun is about 700,000 kilometers, which is about 100 Earth diameters, 100 Earth radii. And the luminosity of the sun is about 4 times 10 to the 26 watts, which is much more than the human race puts out in trillions of years. The temperature is about almost 5,800 Kelvin, and half of the core the core in the hydrogen has been fused to helium at this point. So there's an enormously large inert helium core in the center of the sun today. And the sun right now is in a state of hydrostatic and thermal equilibrium, meaning that energy that's coming out the surface is being balanced by energy being produced in the core, and the sun's not getting radically larger or smaller. It's not pulsing in any way, literally radially pulsing in and out. So it's in both hydrostatic and thermal equilibrium. So during its main sequence life, we have the convective zone on the outside, radiative zone between that and the core, and the inert core right now. And the inert core is actually small compared to the hydrogen-burning core, but that would comprise about half of the mass of the core, that purple nugget in the center. So as the sun evolved, it started off as the top one, where we see that it was about 75% hydrogen, about 25% helium, or more like 85% hydrogen, 25% helium. That's kind of what it is at the sun's helium abundance by percent of each element. So that would be the total number of elements per particle would be what we're looking at now, and rather than by mass, because if it was by mass, it would be about 75. But we're looking at per particle. About right now, the distance from the core shows you what the helium nugget looks like. And we see that it kind of is a smooth distribution from the middle thing, meaning with the core has a certain diameter, and that's where the helium is, and that's how we're kind of defining the core, is where fusion reactions occur and where the helium is building up. So the center has a little bit less helium because it's so incredibly hot that some of that's getting driven out a little bit. But after about 10 billion years, the core will expand, and it will be then all of the hydrogen will be gone in the core. And there will be literally none in the core of hydrogen. But the helium will then be layered on top, and that little nugget will be extraordinarily large at 10 billion years. But even still after 10 billion years, most of the star is made out of hydrogen. And if we think the size of the sun is about 700,000 kilometers, even at the surface, we won't see an abundance of helium percolating up. That's because there is no mixing from the core up to the surface for stars like the sun. Remember, between the core and the outer regions is a radiative zone where there's not a lot of flow, where the photons just travel radiatively rather than convectively. So right around 350,000 kilometers from the core, it still is flowing radiatively. Energy flows radiatively. There's not a lot of burbling and bubbling. That only happens at the top layers, right around 500,000 kilometers or 400,000 kilometers and up, where the convective layers live in the sun. So there is no mixing of the core helium to the surface. All right, so as the sun runs out of hydrogen, we're going to kind of repeat this a couple times. It's just the nature of this particular talk. We'll repeat things a couple times. The helium core collapses, meaning it starts to get smaller and smaller and smaller, and it heats up. And it heats up extraordinarily rapidly, but it does not actually ignite helium fusion. The hydrogen burns in a zone around the core. It's a very thin shell around it because there's no hydrogen left in the core. And that means because there's less of an area where it's actually occurring, less of a volume, then the fusion, in order to produce the heat, in order to stay in equilibrium, it has to go faster. If it has to go faster, it has to get hotter. In order for it to get hotter, that means greater luminosity. If it has greater luminosity, then the star must expand. And so therefore, the star starts to grow in order to accommodate the increased luminosity coming out of the core. And so therefore, it becomes a red giant. So by the time it becomes a red giant, there's an enormous envelope around it. There's a hydrogen-burning shell and an inert helium core that's not yet burning, or at least fusing helium into anything. So that's interesting. Let's describe that again in more detail in a second. So at an age of about almost 11 billion years, about 6.25 gigayears, 6.35 gigayears from today, it'll run out of hydrogen. Most of the volume of the core is helium, and the core will contract because the pressure of the star above it is heavy, and so it's pushing it together in order to, because the core will contract such that the volume around it can actually contain only hydrogen, which then participates in the hydrogen burning in a shell around the core. So at the surface, the temperature is going to drop, even though the core temperature is going to rise. And that's because the luminosity increases by a factor of almost 2, or twice as much, 2.21 times. So if the luminosity increases twice as much, that means the core luminosity has to go up. For the core luminosity to go up, that means the temperature must go up. So it's getting hotter in the center of the sun all this time. It becomes a subgiant star. Next, over the next 700 million years, or almost about a half a billion years, the sun will expand at roughly the same luminosity, and it'll become, it'll stay about two solar luminosities, then it'll swell in size, and then all of a sudden it'll start to grow really fast. And it'll become an extraordinarily fast-growing red giant star. And as it does so, it'll puff up in size. And the radius of the sun will go from 1.5 times its current radius, which is 700,000 kilometers. And so 1.5 times that is almost 1 billion kilometers. It's more than 1 billion kilometers, up to twice it, 2.5 times it. So it'll go from 750,000 kilometers all the way up to 1.5 or 1.7 billion kilometers, which is really a large star now because it's twice the radius, 2.25 times the radius. Since it expands, the surface temperature cools, but the luminosity, remember, is large because the core temperature is high, so the luminosity is great. All right. So it'll climb the red giant branch, take another 600,000 years to get larger and larger and larger as the core contracts and contracts and contracts and gets hotter and hotter, and the shell burning goes even faster and faster. And during this time, this red giant phase, the surface temperature, the surface will not be as bound as it is today. Remember we talked about the solar wind when we talked about the sun. The sun always has a solar wind, but now the solar wind will be incredibly strong, and it will lose about 1/4 of its mass out to a wind pushing it away. So most of the sun will start falling apart. A big chunk of it, 1/4 of the mass, will be gone. And that's because as it expands, it's farther away from the center of gravity, which means if it gets energy, it's easier for it to escape. And all you have to do is get it hot enough so that it escapes. So there will be huge pulses of clouds that will come off the sun in an enormous, enormous wind as it becomes a red giant. So remember again, the helium core contracts and heats, but still doesn't participate in fusion. But what's happening in the core is the electrons become a degenerate gas. And that means they're basically stacking up on top of each other, unable to move, both physically in place and even relax any of their energy. So they actually get packed down to such an extent that it's almost like they don't have a temperature. They almost get to the point where they're stacked like bricks. So the electrons are almost incapable of moving. So it's almost like they have no temperature. The protons, though, are more massive, so they actually act like a normal gas, and so they get hotter and hotter and hotter. But the hydrogen burning becomes a shell around that core, which is now a degenerate electron gas, which is a funny thing to say. And the huge puffy envelope of the star becomes almost the size of the orbit of Venus. So Mercury is gone. It's dead. It's been eaten by the sun. And if it gets out to the size of Venus, then Venus is dead. It'll go into the sun, and that's the end of the planet Venus. Likewise, that's probably the end of the planet Earth too, because once you get to that size, there'll be a huge amount of wind that'll drag on the Earth. It'll provide friction, and as the Earth travels through this enormous wind of gas coming off the sun, it will spiral into the sun at this time and disappear as part of it. So the inner solar system will be cleared of planets at this time. including the Earth. So this is how the Earth dies. So at the tip of the red giant branch, isn't that a funny thing to say? That's such a terrible thing to say, but that's what we're going to say. The Earth is dead when the sun becomes a red giant. So the tip finally becomes the tip of a red giant branch. A huge change occurs, and the core of the temperature has been getting hotter and hotter and hotter, and finally it reaches about 100 million Kelvin, and that ignites all of the helium burning all at once in what we call the helium flash. And this happens when the sun has cooled at its surface to become an M0 star. It's a giant star, and the temperature has dropped to well about 3,000 Kelvin, about half its current temperature. But the luminosity is now almost 2,000 times that, and the radius is almost 200 times its current radius. And that's big. That's about 3/4 of an AU. That'll swallow Mercury. That'll swallow Venus. That'll be the end of that. So that's a big, big, big star. Red giants are big things. So now the sun is a red giant at this late stage in its life. And when it does reach that, all of the helium starts burning carbon to oxygen, ignite extraordinarily rapidly in what's called the helium flash. And the helium flash occurs because the protons are getting hotter and hotter and hotter. They're moving faster and faster. The electrons are getting more and more and more compressed. They can't move. And so they're in what's called a degenerate state. This degenerate state needs to be lifted away when it gets hot enough so that when fusion starts to occur, it releases more energy, which can be given to the electrons, and therefore they can participate in the support of the star. And so now we go after the helium flash, where this all begins at once. We then move down to what's called the helium main sequence, or the horizontal branch. So once again, the triple alpha process now is coming into play, which is at 100 million Kelvin. The triple alpha process, which is the fusion of helium nuclei into carbon and then into oxygen. The first step is to slam two alpha particles, which are helium nuclei, together. They form beryllium, which is incredibly unstable and will disintegrate almost immediately. But if the density is high enough and another helium nuclei comes along fast enough, then they'll collide together to form carbon-12. And carbon-12 then can collide with another helium nuclei to form oxygen-16. So these little starry things indicate collisions, and beryllium can fall backwards and forwards. It can go from this and into the other. So beryllium is very short-lived. It's barely together. And only thing that's producing energy out of this thing is the collision of the beryllium with another helium nucleus to give a gamma ray photon, or the carbon nucleus with a helium nucleus to form an oxygen nucleus, which also gives gamma rays. And those gamma rays are what thing that actually provides the energy. So the star then is hot enough to burn the helium, but this is not efficient. It's not even remotely as efficient at producing energy as hydrogen fusion into helium. So you get all this additional hydrogen burning around. You get core helium fusion, which is extraordinarily sensitive to temperature. Then you have hydrogen burning around the shell, and the star shrinks a bit because now it can shrink. So as it shrinks, it raises the temperature. It shrinks in radius, it gets fainter, and it goes back to hydrostatic and thermal equilibrium again, using triple alpha process as its primary source of energy. The sun descends back onto the horizontal giant branch about 1 million years. The internal structure rearranges rather rapidly to accommodate the energy, and now the helium is burning at the core. It stabilizes everything against the collapse. And then there's still some hydrogen burning around because, the star is mostly hydrogen on the outside. It's lost most of it. It's lost 1/4 of its mass so far. We're down to a 0.75 solar mass star, but that's still hot enough to burn helium in the core as it gets compressed and compressed and compressed. Again, here's our view of it, the triple alpha process. It's incredibly inefficient. It can only last about 100 million years, as opposed to the 10 billion year lifespan of hydrogen burning. That's because this process doesn't give off as much energy, and there's fewer particles now. Remember, there was like a bunch of protons, but now all those protons have formed an object that has 4 objects in it. So now 4 objects, you can think of them as bundles of 4. So you used to have bundles of 1, which became bundles of 4. And now you have bundles of 4 becoming bundles of 12 and 16, so you're rapidly removing particles from the system. The total number of particles is dropping rapidly because as you fuse them together, the numbers reduce. The total number of objects reduce, and because now they're sticking together. But they're still too cool to ignite the carbon fusion, significant carbon fusion into oxygen, but there's some oxygen fusion. And there's very little carbon and oxygen, nothing going much past oxygen at this point. So this is the horizontal giant branch for helium fusion for the sun. Now at this time, the sun's radius will be about 10 times its current radius. The temperature will still be much cooler than it was on the main sequence, but its luminosity will be about 40 times its current luminosity. So it'll still be much brighter than it was. It'll be much bigger than it was, and that's the nature of a horizontal giant branch star. These are all giant stars, which are not main sequence stars, but the main sequence we're talking about now is a main sequence for helium burning, not a main, which is the horizontal branch, not a main sequence of hydrogen burning. The helium fusion is much less efficient, so it can only last it'll last a much shorter period of time, only 100 megayears or 100 million years. After this 100 million years, it again slips out of equilibrium. The carbon-oxygen core, ash core, begins to contract, just like the helium core did previously. And then there's a helium-burning shell around that core, and then a hydrogen-burning shell around that helium-burning shell. So it's a little bit of an onion shape. It swells up again, becoming a giant once again, raises its radius to about 20 times the radius of the sun, cools off some more, luminosity grows again. Remember, the luminosity is a result of the temperature increasing. So the higher the temperature in the core, that provides greater luminosity in the core. Greater luminosity in the core means the rate of reaction is going faster in the core because stuff is running out. And so they're trying, the reason the luminosity goes up is because since the temperature must go up because there's fewer particles, the particles have to move faster in order to literally find each other and in order to do the fusion. Since there's fewer particles with which they can collide, they must go faster, which means they have to go farther, literally farther inside the star at a faster speed in order to collide with each other so they can actually provide the energy to balance against gravity. So it's a big race. It's a huge race against gravity and the pressure due to gravity. So it again climbs up what we call the asymptotic giant branch, and over 20 million years, the carbon-oxygen core contracts and contracts and contracts even more and heats up even more. The fusion moves out into a very strong shell. The thin hydrogen shell is way outside the helium-burning shell. And on the outside, the sun swells up, gets even bigger, gets almost as large as the Earth's orbit, gets to be about 84% of the Earth's orbit. The Earth's been gone long anyway. It went down the first time, but now it's probably Mars's turn to go under, even though it's at 1.5 AU. There'll be enough drag from the wind from the star they'll probably plunge into. And the temperature will again cool off at the surface to 3200 Kelvin. But the luminosity is much greater. So the high luminosity belies the incredible temperature at the core. So even though the surface temperature is only 3000 Kelvin, the core temperature is well over 100 million Kelvin. And it's even brighter than it was when it climbed the giant branch before. And again, because it's brighter, it will live a much shorter time span on this thing. All right. So then after 100,000 years, again, it collapses and forms that shell. There's the helium shell burning on top of it. There's the asymptotic giant branch. So we're looking at it as a thin line instead. And we're watching it track across the HR diagram. So this is what we call an evolutionary track. The main sequence line that's going from upper left to lower right is just a reference point. But the black line that leaves the main sequence goes up the red giant branch to the horizontal branch and then up the asymptotic giant branch. That's the track of evolution for the sun. And so each of those things goes different rates of speed along those tracks, but that's the track it would take if we could watch its luminosity and temperature change from a safe distance as the star evolved over billions of years. All right, so once it gets the asymptotic giant branch, it is now a red giant for the second time. It's cooler, larger, and more luminous. And there's an enormous inert carbon and oxygen core with a helium burning shell around it, hydrogen burning shell around it. And the red giant envelope is, of course, enormous at about 200 times the radius of the current sun now. What's funny about this is helium burning is incredibly sensitive. So to actually make that ash, that green ash with carbon and oxygen in the core and the purple area that we see there, it's incredibly temperature sensitive. And so the fusion rate goes like the temperature to the 40th power. So if you raise the temperature only by a little bit, maybe 10% when it's 100 million Kelvin, then the fusion rate goes up 45 times. And if the temperature doubles, it'll go up, wow, almost a quadrillion times. So that's a huge, huge, huge jump in fusion rate. So if you increase the temperature just a little bit, you get these enormous, enormous changes in the rate of production. So a small change makes these thermal pulses. So I made those arrows to show that all of a sudden there's enormous heat that all of a sudden pushes out from the center, lifting the envelope away, and it destabilizes the envelope of the star, and that makes the core and the envelope separate. And as a result of it, the entire outer envelope is ejected as a fast wind over 100,000 years. Which is essentially the entire lifespan of known human history, is about 100,000 years. The carbon-oxygen core continues to contract, but outside of that is an enormous, brightening, hot, moving shell, and it'll take about 5 or 6 or just a half a dozen or a handful of these pulses to completely separate the outer shell of the star into the cosmos. But the star's core still stays there. It's still remaining super duper hot. It just never, and it doesn't get bigger because it's pushed together now. It's now a huge thing. It's self-gravitating. It's not going to just expand because it's gas. No, it's going to be, it's very, very, very dense. It's extraordinarily small. It's been pushed together, and the temperature is incredibly high. However, it's not so high that carbon fusion ignition occurs, which occurs for much, much, much higher temperatures. So the asymptotic giant branch phase exhibits enormous mass loss as a result of these thermal pulses. And now we're down to about 60% of the original mass. So now 40% of the sun's mass is now gone, with the quarter of it gone in the initial part. So we've got expanding shells in the first group, and now we have even more expanding shells of hydrogen gas and some carbon and some helium puffing away, because those thermal pulses do bounce a little bit off the bottom for some stars. And so we see the enormous mass loss coming off of the star. Then, so there'll be about 4 or 5 or 6 puffs, maybe up to 7, depending on the computer model, and roughly about 100,000 years between them. And each puff sends the sun to a much, much larger radius. The sun contracts and contracts and contracts, and then all of a sudden it blows the outer layer off as it gets just hot enough in order to do so. And that's because of that enormous temperature gradient that I showed you, or the temperature sensitivity that I showed you. So it contracts and makes like a really tight blanket, and then just like a little kid who has tons and tons and tons of blankets on just kicks them all off. And that's what it does. It's a kicking off of all your blankets, and it pushes them off the bed, basically. And so they go out into space, and they're left out with something, with the remaining envelope expands away. The last of the thermal pulses pushes what's left of the outer envelope over the course of a couple thousand years, and it's left with the bare carbon-oxygen core down there. So the surface of the sun, the luminosity, the shell goes from about the star from the outside. The envelope looks like about 4,000 Kelvin, shielding the inner core. And now we see the bare core of the star, which is over 100,000 Kelvin. And the luminosity stays roughly about constant. It's about almost 3,500 times the luminosity of the sun, between both the glowing material that's coming off of it and the core of the star that remains. And the outer glowing shell is called a planetary nebula, and that's kind of a funny term. But the bare core then ionizes the outer shell. All of the atoms become ionized. They're very diffuse, and so they emit specific. They make an emission spectrum. And the emission spectrum is called of the gas is called a planetary nebula. And so this is the state of affairs after 12 billion years of the sun's history. The expanding envelope it forms a nebula around the contracting core, and that's ionized by the central core, and that thing just goes out into space and becomes nothing, and you mixes with the rest of the interstellar medium. So this hydrogen, some of the helium, and a little bit of the carbon and oxygen that was in the core gets diffused out into the cosmos and becomes part of the interstellar medium again by these thermal pulses of the sun, or what that it will do, and that will be the seeds of future stars. And the star becomes a host to a planetary nebula, and the carbon-oxygen core is exposed, and that's called a white dwarf. So the planetary nebula then is the glowing outer shell that I showed you before, plus that like flowery shape, and these things are seen in the sky. And one of the most prominent ones is called the Ring Nebula, which is in the constellation of Lyra. And you see the glowing gas around it, and the white dwarf in the center. And the glowing gas used to be the envelope of the star, and the white dwarf is the thing that's ionizing it at the core. That's the core of the star, and that's over 100,000 degrees Kelvin. 100,000 Kelvin. I shouldn't say degrees Kelvin. It's just 100,000 Kelvin. That's so incredibly hot that it's ionizing all that gas. And that gas then glows as a result of it being irradiated by the huge amount of ultraviolet photons coming off of the white dwarf. And then the atoms, and they're atoms now, pick up the electrons, take that ultraviolet photon, are ionized from the atom, and as they cascade back down into the atom to be reabsorbed or combined back to atoms, then it gives off the light that we see from the Ring Nebula. And this was taken, this is called M57. This is one of the great images by the Hubble Space Telescope, and this is a Hubble Heritage image. And it's kind of a funny thing. If we look, there's a special filter called an O3 filter that you can get for a telescope. And if you look at planetary nebula with it, they're actually much clearer with this filter. And that filter allows you to actually see these nebulae and pick them out a little easier in a telescope if you're using it. Also, there's a number of there's lots of ionized nitrogen in this field, as well as ionized helium, and so forth. And so this bubble shape is what we expect from something like a planetary nebula from a star that's dying. And there's another one, which is the Helix Nebula, one of the more prominent planetary nebulae. It's enormous, about 700 light years away, and the size is across it is about 3 light years. So as the star is expanding away, or the outer layers are expanding away, the white dwarf at the center is so incredibly intense and ultraviolet light that it can ionize gas out to a distance of 3 light years. So once again, if you happen to take a spaceship and fly right next to that white dwarf right now, take the Doctor Who TARDIS and go over there and open up the gas, the air inside of your spaceship would be ionized and turned to a plasma ionized gas inside your spaceship, and your skin would be slowly ionized and evaporate away. Yeah, another name for astronomy classes is A Million Ways to Die, which is kind of a funny name. But the Helix Nebula is also a wonderful target for telescopes, and this was taken by the Hubble Space Telescope. Here are other photos of planetary nebulae, and planetary nebulae are incredibly important things because they tell us about how stars die, and they also tell us about maybe there's a stellar companion, because some of these things have these strange curlicue type shapes, which might be occurring because there's a secondary companion that is interfering with the expansion of the gas, or maybe the star itself was rotating incredibly quickly, or the thermal pulses were not even from the center, and they were not smoothly distributed across the white dwarf as the thermal pulses were occurring. So it's an area of active study as to exactly how planetary nebulae form, and there's some really amazing things, and they're fun to find in telescopes. And this was taken by the Hubble Space Telescope after the 2009 servicing mission. And this is the Bug Nebula, or NGC 6302. And the winds from these, we think, oh, just a stellar wind, wada, wada, wada. No, these winds can go incredibly fast, up to 600 or 1,000 kilometers per second. So these winds, while they look very gossamer, are actually more terrifyingly fierce than the nastiest hurricane that's ever been unleashed on the surface of the Earth. At these winds at 600 kilometers per second with a white dwarf that would ionize everything within light years of its location. And that's actually one that can be seen in the sky if you know where to look in the constellation Scorpius. So it's kind of better if you're more in the southerly locations, or if you're in the southern hemisphere, to kind of take a look at it. So as the white dwarf contracts, it becomes incredibly dense, and it is now a degenerate electron gas, which basically holds it up against the pressure of gravity. So the pressure becomes independent of the temperature. We'll talk about that pretty soon next time when we talk about the nature of degenerate gases, when I talk specifically about white dwarfs. So the pressure grows incredibly rapidly and can counteract gravity. So degenerate electron gas has the capacity to hold up an entire star. And when the star will collapse and collapse and collapse and collapse and emit more and more and more heat until it gets down to about 1/10 the current radius of the sun, or about the size of the Earth. And then that's all it does. It's just a hot, small body that's the core of a dead star. And this degenerate core is now a white dwarf. It's about half the mass of the sun, so the sun has lost almost half of its entire mass into space as a result of the planetary nebula phase and the asymptotic giant branch phase. And it just simply cools. And it takes a long time for them to cool because white dwarfs are so small that they might be incredibly hot, but they're not very luminous. They're not luminous because their size is so small. Remember the luminosity equation where we said the luminosity of a star is proportional to the surface area squared, the surface area, and the temperature to the fourth. Well, these things are incredibly hot, but they're also really small. So they don't emit, they're very dim by comparison, and so they're hard to find. And therefore, what we expect to see is that they will take a long time to cool because the surface area is so small that the energy simply can't get out. And it'll take up to 1 trillion years to fade away and stop glowing. And since the universe is only 13.8 billion years old, not a single white dwarf has turned into a black dwarf. A black dwarf is a white dwarf that has cooled completely off. The universe simply is not old enough for white dwarfs to have ever cooled off. So every white dwarf that's ever been formed in the history of the entire universe still is a white dwarf and still is incredibly hot and still is emitting huge amounts of ultraviolet light. So there's our evolutionary track for the sun. The sun starts off as a protostar, becomes, after about 11 billion years in the main sequence, becomes a giant. After it rises to a red giant, has a helium flash, drops back down to burning helium fusion, burning helium on the horizontal giant branch for a while, then goes up the asymptotic giant branch and puffs itself apart. When it puffs itself apart, it makes a planetary nebula, and that reveals the core, which is a white dwarf. So there's our evolutionary cycle for the sun, and each of those stages is shorter and shorter and shorter as it goes, with the planetary nebula being the shortest phase, so we wouldn't expect to see too many planetary nebulae in the sky, and that is exactly the case, because this phase, how long it lives, is a very short period of time. Main sequence stars live the longest, so therefore, when you look in the sky, you see stars not littered with planetary nebulae. If planetary nebulae lived 11 billion years, then we'd have all sorts of little pretty objects all over the place. But as it stands, we've got pretty stars instead. Now, if we then take a look instead, I promised you at the beginning we'd look at the really boring tiny stars and say I could do it all in one slide. Here we go. If you have a small mass star, meaning something that is little less than half the mass of the sun, then why does it last forever? It basically lasts forever. It'll last for up to 1 trillion years, 1,000 gigayears. Why? Because remember the sun, the inert helium core, had no mixing with the surface. But when a small mass star comes together, its temperature in the core is much lower. It's roughly 10 to 12 million Kelvin. And therefore the whole thing's convective. Only the outer layers of the sun are convective, and there's a radiative area that blocks the convection to flow from the surface all the way to the core. But in these little stars, they're fully convective throughout. Once it's like about less than 0.4 times the mass of the sun. And the surface goes all the way to the core, and you have convective cycles that reach to the core. So the entire star then can partake in the helium, in the hydrogen to helium fusion. And because of that, that allows the star to be basically a slow cooking pot. So you think of those slow cookers where you say, oh yeah, just put in the soup and then come back at the end of the day and your soup's done, right? These are those. These are the slow cookers of the universe. And they live 1 trillion years. There's not a single M dwarf type star that has ever died in the history of the universe, because the universe is only 13.8 billion years old, and these will live 1 trillion years, which is 1,000 billion years. So, yeah, these are very simple little things, but remember that most of the stars in the sky are half a solar mass or less. Roughly 70% of all the stars in the sky do this, but they're very, very, very faint and very underluminous. So when we look out at the night sky, we don't see hardly any of these stars. Any of the M-type stars that we see in the sky with either binoculars or a telescope with ease are giants. All the other stars that you see in the sky are bright, bright, bright OBAF, G, and K type stars in the sky. So that's what we have for our HR diagram. We have all sorts of stars up and down the main sequence. We have supergiants, giants, and white dwarfs. That's where they come from. So this version of the HR diagram and what we saw with the Gaia mission and so forth, the reason these blocks appear in there is because the stars, there's literally billions of stars, hundreds of billions of stars, and hundreds of millions have been cataloged in their spectral type and their luminosity class. And therefore we catch the stars at their various stages in life. So when we look at most stars, we see most of the stars in the main sequence because the main sequence is the dominant lifespan of a star. When we catch a star when it's a giant, it's just leaving the main sequence. When we catch stars that are supergiants, we're looking at the most massive stars. And white dwarfs have gone through their life cycle. But anything about less than half the mass of the sun, on this graph, say 61 Cygni A or B, or less than 0.3 times the mass of the sun, those things, there's not a single star in that group that's there, which comprises 70% of all the stars in the sky, has ever died. So they're the ones that will be around for pretty much the entire universe. They will get to see it. And that gives us kind of the bottom rung of the life cycles of stars, where the brown dwarfs just stay brown dwarfs. The red dwarfs become, they don't become a red giant. They just collapse and collapse and collapse and eventually become a white dwarf. Whereas the sun becomes a red giant, a planetary nebula, and then ends as a white dwarf. And next time, we'll talk about the more massive stars. The stars much more massive than the sun, where all the other elements in the periodic table come from. Where all the carbon, nitrogen, oxygen, where the platinum, gold, uranium, lead, every other element in the periodic table that lives as part of the planet Earth, that makes up the Earth, silicon, iron, everything, comes from stars that are bigger than the sun. So we're going to see what those do next time. Today we're going to talk about the exploding stars, the biggest stars in the universe. These are the ones that provide us with all the heavy metals that we see and use, the aluminum that makes up your computer, the iron in your blood, and the gold in your wedding band. Anyway, we're talking today about the evolution of high mass stars, how they live, how they are born, and how they die. Again, let's go back and we can go back to look at the fiducial idea. The top area shows exactly how the sun evolves from a protostar. It has a long main sequence lifespan of about 10 or 11 billion years. It swells up into a red giant, puffs off its outer layers with a planetary nebula, revealing the core as a white dwarf. And we see these things from the left-hand side, which is a star-forming region with the Horsehead Nebula in the middle, and then in the middle picture we've got a globular cluster in the lower right and a beautiful open cluster in the open left, which is the remnant of a new batch of stars. And over on the right is the Ring Nebula, which is a planetary nebula surrounding a tiny, tiny, tiny white dwarf star that illuminates it and causes it to glow by ionizing. But that's a story for stars like the sun that live about 11 or 12 billion years. We're going to look at more massive stars. Hot stars like O and B type stars, basically their masses are greater than about 4 solar masses. They burn extraordinarily hot, they live extremely fast lives, and they die very young. So their main sequence phase, they do burn hydrogen into helium in their cores just through a different process, not the proton-proton chain, but through the CNO cycle. They also build up a helium nugget in the core for their main sequence phase, because that's the definition of a main sequence phase, is hydrogen to helium burning. And they do this just like any other star. The main sequence is where stars burn hydrogen into helium. But for high mass stars, this lasts at most about 10 million or so years. So let's look at one of the more fiducial stars of this type in the sky. You know it by sight in the stars, but this is an artistic view of the star Betelgeuse. And Betelgeuse is a nearby supergiant red star in the constellation of Orion. This is a beautiful piece of artwork by El Calzada at European Southern Observatory. And this is a wonderful picture by Babak Tafrishi of the constellation Orion above the Very Large Telescope Array down in Chile. And so what we see is the belt of Orion up there, and because we're in the southern hemisphere, Orion's inverted. So just above the telescope, the bright red star is the star Betelgeuse. And Betelgeuse, this is a picture, is a massive, not an artistic picture, but rather this is a massive array of pictures put together as a mosaic by Rogelio Bernal Andreu, and it was featured in Astronomy Picture of the Day in 2010. So Betelgeuse is the upper left shoulder of the giant of Orion. And there's all sorts of wonderful things going on in the Orion Nebula and the Orion area of the sky. But Betelgeuse is the star we're going to be talking about, which is this bright star. Betelgeuse is a red supergiant star. It lies in the upper right area of the HR diagram with a spectral type of M and a luminosity of about 100,000 times that of the Sun. And it's about the same temperature as little red dwarf stars on the main sequence, or giants like Aldebaran, but it's much, much, much larger. And Betelgeuse is brighter, and we call it a red giant because it's brighter at red wavelengths compared to blue wavelengths of light. And so this is a sample type M-type star that we might get from I forget exactly where, I grabbed this from the Sloan Digital Sky Survey. And this particular thing shows an M-type star, and the wavelength band is from 4,000 angstroms to 7,000 angstroms, which spans the visible light. So to your eye, this is the part that is visible to your eye, and so I kind of grayed out the rest to the right. But you can see it actually glows a lot in the infrared. But for visible light, it's brighter in the red wavelengths than it is in the blue, and has striking absorption features and so forth. And because it's bright in the red compared to the blue, that's why it looks red in the sky. Now we can also judge whether it's a giant or a main sequence star by looking at these absorption features of the dips from the continuum. You can imagine that this is actually some sort of continuum that goes over the top with lots and lots and lots of dips that go through. So where the peaks are is where the continuum is. So you could draw a line across the peaks of the continuum and then imagine that it's actually that the absorption lines are huge absorption lines down from the peaks, where the peaks go up to the continuum. And so you see they're very, very, very wide peaks, very wide absorption features. And if they're comparatively narrow lines, when there's only one or two, then it's called a giant star. And if they're wide absorption lines, then it's a main sequence star, because main sequence stars are compact, so therefore they have a lot more Doppler broadening. The atoms and molecules are moving faster, so therefore the widths of the lines are broader. And in a giant star, the widths of the lines are narrower because the pressure is lower. And because the pressure is lower, there's less movement of the atoms, and the atoms can only absorb it near the frequency where they're absorbed. But if they have under high pressure, they're moving faster, and so you can get Doppler shifts for the absorption. Anyway, so from the spectrum, which gives you the line widths, and the color, which gives you the temperature, you can deduce that this is a supergiant type star, and of spectral class M. Now, how do we know it's really that big? I mean, what we can do is, remember, we can also take, if we have a handle on the luminosity, remember there's a luminosity relationship for the Stefan Boltzmann relationship, where the luminosity is equal to the surface area times the temperature to the fourth power. So if we have a way of measuring the absolute luminosity of it somehow, and then we know roughly its radius, then we know its temperature, which is obvious from the spectrum, then we can determine its radius and determine it's an extraordinarily large star. And that's the Stefan Boltzmann relationship. Anyway, we do know that Betelgeuse is an extraordinarily rare star because it's a more massive star than the Sun. So roughly less than a couple of percent, like 2 to 4, like almost 3 or 4% of the stars in the sky are even as or could be as massive as Betelgeuse. Actually more like about 1%. So Betelgeuse is probably much more massive than a 2 to 4 solar mass star. So we're really looking at the the deep, deep, deep little blue sliver where we have a 4 to 8 or 10 solar mass type star, which is about 1% of all the stars in the sky, and Betelgeuse falls in that realm. It's not one of the small mass stars between 1 and 2 or a half or a quarter or less than a quarter of the mass of the sun. It is in that elite category of very, very, very massive stars where so few of them in the sky are that massive star. Now, Betelgeuse is about 152 parsecs away, or about 500 light years, and the luminosity is about 120 times that of the sun, so it's extraordinarily luminous. And that puts it, this is a really fun statistic, the absolute wattage is about 4 times 10 to the 26th watts, and if you compare that to what human civilization puts out, which is about 17 terawatts, we're nothing compared to the luminosity of Betelgeuse. We're nothing. 10 to the 14th times less. Oh my goodness. And the Betelgeuse itself is about 1,200 times that of the sun. That comes from both direct measurements, as we'll see in a second, as well as the Stefan-Boltzmann relationship. And we know that 100 Earths fit across the sun, but about 120 Earths fit across Betelgeuse. That means that it's bigger than the orbit of Jupiter. All right. So let's take some interesting looks. This is a 7 millimeter radio image taken with the Very Large Array down with NRAO, and it was taken in 1998 by Lim, Corelli, White, Beasley, and Marson. And they found that the optical disk of Betelgeuse is this roundish sort of thing in there, but the glow that we see here is a radio emission. Radio emission from Betelgeuse's very diffuse atmosphere. We see that Jupiter's orbit would easily fit inside of this atmosphere of Betelgeuse, and so Jupiter would slowly spiral in. And we see that another thing about Betelgeuse, it's not spherical. It's not a spherical star. So people thought, wow, that's really interesting, 1998. So following up, prior to that, Betelgeuse was measured in terms of its physical size with the Hubble Space Telescope image of a direct imaging by Dupré et al. At Center for Astrophysics using the Hubble Space Telescope. And this is a direct image of Betelgeuse. We see that the star is actually quite large. It's much larger than Earth's orbit, much larger than Jupiter's orbit. So Betelgeuse is this enormous, 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 physically large star. Now, a group at the European Southern Observatory took a series of images and then placed them inside using the VLT and infrared imaging as well as optical imaging to try to determine the actual dimensions of it. And if we take the little red dot that's in Dupré's image from before, it would just fit inside that red circle, just barely. And you can see that there's kind of plume-like structures that are visible in the infrared. Now, the right-hand side, this plumey sort of thing, is an infrared image. Remember these types, as we saw gently in the other spectrum that we saw before, that the vast majority of the emission from this star is actually in infrared. So, because it's a cool, large star, and since it's cool, the dominant radiation is infrared. Well, it's also puffy. There's a plume shooting off to the side. There's also other plumes kind of noodling around. It's a really distorted thing, and it's not actually spherical the way we think of this, like the sun. The sun is spherical, but we can really think of Betelgeuse as not even spherical. It's just this pumpy sort of thing. And it's an incredibly sharp image. This was taken by the Very Large Telescope in Chile, which is that set of telescopes that we saw from Babak Tafrishi's image from before. And we're actually seeing this unknown plume to the right. What's funny is the individual pixels are as small as 37 milliarcseconds, which is about the same size as a tennis ball viewed from the ground at the International Space Station, and is all near-infrared imaging. And if we then zoom out with a different infrared camera, again with the VLT at ESO, we see the black disk is the thing that is used to occult the star because the star is incredibly bright. It's one of the brightest stars in the sky. And so to actually get the image of material surrounding it, you need to actually block it out. So that black disk is actually what we call a coronagraph, or some sort of, it'll block the light from the star so that so it'll occults it and puts a little disk in front of it so you can actually see the dim stuff around it. And the previous image was put in the center, and the disk-like image that we see from Dupré's images is the red circle in the middle. And now we zoom out to show the full grandeur of Betelgeuse, which really doesn't actually seem like much of a star anymore. It seems like a star nebula thing sort of thing. And if you actually were to take a spaceship and fly over near Betelgeuse, you would find that you'd fly into this cloud-like structure that got brighter and brighter and brighter towards the center. You'd fly by globs of mass that's moving out with enormous winds that would buffet your spacecraft as you tried to get closer and closer. And eventually you'd find yourself in an incredibly bright, foggy mist and get closer and closer to the star. And you would just all of a sudden be close to what would be bright enough that we would call the photosphere. So many of the absorption features that are found in Betelgeuse's spectrum come from this expanding shell of gas that comes off of the star itself. So Betelgeuse is shedding a lot of mass. And just like we saw last time in the low mass stars, how we had a star like the Sun puffs itself apart and forms a planetary nebula, Betelgeuse isn't waiting. It's not done yet with its life before it starts really puffing itself apart, as all high mass stars do. And that means because it's puffing and moving, it's variable. So it's an actual variable star, which is easily seen with binoculars. So if you want to go out in the night sky and take a pair of binoculars and see what the variation in magnitude is, this has come from the American Association of Variable Star Observers. This is their data, and it's compiled by a number of observers, and these observers then submit their data to the AA VSO. You can become a member too. It doesn't cost you. Well, it costs you a little bit, like $20 a year. But then you get to submit your data into this set, and you can make meaningful science measurements just with binoculars, specifically of this star. But as you can see, the star varies as time progresses from left to right. We see that the brightness and magnitudes varies pretty big. It can vary up to a magnitude in brightness. As you can see, roughly about 2008 or 2009, it was pretty dim, and then it brightened it went as dim as magnitude 1, and by about a couple years later, it was as bright as magnitude 0.01, almost a zero magnitude star, and it's been brightening and dimming by about a quarter of a magnitude fairly regularly as it puffs itself apart. So Betelgeuse is an extraordinarily variable star, and it's fun to observe. So I would invite you to use this as one of your primary variable stars if you want to observe them and do some science in your own home. This is a great way to do it, and you can learn how to do this by going to the American Association of Variable Star Observers. You don't have to become a member to submit your data, but they always appreciate that you do. All right, so stars themselves can be extraordinarily big, as we've seen in the past. The Sun is only about 700,000 kilometers across, and so on this image it's really tiny, and the bright star Arcturus, which is in the constellation of Bootes, is much larger than the Sun, almost 20 times larger, 30 times larger, about 30 times larger. And if we then look at the red supergiant Antares in Scorpius, it's extraordinarily large, larger than the orbit of Mars. And so these are the red supergiants. So red supergiants exist, like Betelgeuse. So how do they live? Well, they're so big, they're so massive. So a large physical star like a red supergiant doesn't mean it starts like that. It started as a main sequence star and swelled up. But while it was on the main sequence, it burned hydrogen to helium. But it does not do so. But these massive stars, any star more massive than about 4 times the mass of the Sun, does not use the proton-proton chain to fuse hydrogen to helium. It uses the CNO cycle. It does fuse 4 protons. You can see the equations. These are a set of reactions. Where a proton, P, combines with a carbon-12 nucleus, they collide together, and the arrow says the output is a nitrogen-13, or a light nitrogen nucleus, and that emits light in the form of a gamma ray. That's what that little YE sort of image is. That's a gamma ray. So the next step in the CNO cycle is that the nitrogen-13 nitrogen decays. One of the neutrons decays to become a carbon nucleus, heavy carbon 13, and it emits a neutrino and a positron, which is an anti-electron, which then slams into an electron and forms more light. But then the carbon-13 then collides rapidly with another proton, which forms nitrogen-14. So we're back to nitrogen again, and that emits light in the form of gamma rays. And then that nitrogen gets slammed by a proton, and it forms oxygen-15, which itself is radioactive and unstable, falls apart to nitrogen-15, which is briefly stable, and that emits again another positron and a neutrino, and then that gets slammed by another proton, and that forms the chain, which returns it back to a carbon-12 nucleus, and that spits out a helium nucleus. So we can add all this stuff together. Basically, 16 objects. So the proton could be something about 1 in the upper left. So 16 things go together to make a carbon-12 and a helium. But notice that the carbon-12 acts as a catalyst. It returns back to the beginning of the cycle, having been used up, and the intermediate processes of creating nitrogen and oxygen along the way. So it doesn't really go anywhere. So it acts as a catalyst. And that catalytic reaction keeps the carbon going, and this is an incredibly important element. So for the sun does a little bit of this. About 2% of the sun's output comes from this. But once you get above 1.1 solar masses, or just a little bit more massive than the sun, CNO is about 50%. But once you're up to about 4 solar masses, it is 100%. So by 2 solar masses, you're doing a CNO cycle completely. Now, this is, of course, inefficient, but it's really interesting to return to the idea that what does fusion energy give you? Remember, when you fuse 1 gram of hydrogen into 0.993 grams of helium, it loses mass. Some of the mass of the 4 hydrogen nuclei, those 4 protons, gets converted into energy. About 0.7% of a gram gets converted into energy. And for every single one of those things, that provides 6 times 10 to the 18th ergs, which is a large amount of stuff. And that's a huge amount of energy by comparison. Just to do this one interaction, that was enough energy to lift about 30,000 tons, 64,000 tons of rock up to a height of 1 kilometer. So basically, just fusing 1 gram of hydrogen into helium is enough energy to take a building and throw it into the air about a mile. That's what fusion energy gives you. So if someday we can figure out how to do this safely and efficiently, we could replace pretty much all of our energy needs with fusion if we can figure out how to do that, which would be pretty cool. Anyway, so just like low mass stars, no party lasts forever, and every star, no matter what is big or small, population 1 type stars, which are young stars that have come through reprocessed material, have roughly about, by abundance, is about 10% by numeric abundance is helium, but then about 90% by abundance, meaning the number of particles, is about 90% of the particles are hydrogen. And by about 5 billion years after the sun's converted about half of its mass into helium, and by about 10 billion years, the sun specifically, now we're not talking just going back to the sun just to get reference frame, the sun will have converted all of the core material to helium, and a significant fraction, out to about half the star's core, will be helium. Now, that's what happens in the sun. A very similar thing happens in every main sequence star. It builds up this nugget of helium in the core, and when that runs out, it's over. And it doesn't matter whether it's using the proton-proton chain, which is the upper left, or the CNO cycle, which is the upper right. Those are the 2 dominant ways that hydrogen gets fused into helium inside of stars on the main sequence. That's the way it's done. There's other things then will come later, which is the triple alpha process. We described that when we talked about the sun, when the sun started dying, and that happens too. But even that doesn't last. Helium fusion doesn't last because you run out of stuff too. Anyway, so what will happen to a massive star that is way up the main sequence, that's an O and B type star, when it starts to run out of fuel and it uses up its hydrogen in the core? Once it's exhausted, it does the same dance that the sun would do. The inert helium core contracts down and starts heating up. There's again the hydrogen burning shell around it and around that contracted core, because pressure, gravity pulls the star together, and it just gets compressed and hotter, but it's not participating in fusion because it's not hot enough yet. So hydrogen burning or hydrogen fusion is in the shell around that nugget in the core. And then this huge puffy envelope expands. So these red supergiants, unlike the sun, which just kind of lazily goes up, no, these shoot straight across to supergiant phase, and they get enormous, radically enormous in a very short period of time, less than 1,000,000 years. Now, the funny thing is, along the main sequence, stars don't have a huge radius difference. Pretty much an O-type star in the main sequence is just only a little bit bigger than the sun on the main sequence. The radius isn't that much bigger. But once a massive star runs out of hydrogen, it swells up much larger than the sun will ever get. The sun will never become a supergiant, it'll become a giant star. But these stars become supergiants. Eventually, the star, this supermassive star, gets the core temperature raises to about almost 200 million Kelvin. That's enough to start up helium burning. And helium burning through the triple alpha process, as we showed before, that makes carbon and oxygen. That only lasts, we're in the sun, this would last about 1 billion years. For massive stars, it lasts about 1,000,000 years or less. And then we've got this layering set that happens down in the core, where there's helium burning in the core, then there's hydrogen burning around, and notice that there's no helium flash, because now it's going to be there, when it ignites it smoothly. Stars more massive than about 2.5 times the mass of the sun don't have a helium flash, meaning the star the electrons do not get so compressed in the core that they become degenerate. And the degeneracy never occurs for stars more massive than 2.5 times the mass of the sun, and it starts burning very, very, very gradually. So much more massive stars simply wag back and forth, and they get bigger and smaller, hotter and cooler, and they stay at that extraordinary luminosity, but their surface temperature changes. Now remember, the HR diagram shows the surface temperature. So the surface temperature of a supergiant star ranges between, say, 3,000 Kelvin and maybe 20 or 30,000 or 10 to 20,000 Kelvin. That's a blue supergiant. A blue supergiant isn't really that blue. It's more whitish because it's kind of the same temperature as an A star. Well, I guess an A star is kind of bluish. It will be bluer than the sun. In any event, it becomes a blue supergiant when the helium ignition starts, and then it smoothly moves back into this new framework. So that's producing more energy, which is producing a little bit more luminosity, but that allows the star to actually collapse back down. All right, so when the helium finally runs out in the core, and that doesn't take long, that takes an extraordinarily short period of time. In fact, it doesn't get down to the horizontal branch at all. It just kind of wags back and forth. When it runs out of helium in the core, then the carbon and oxygen core collapses and heats up. And that's a big deal, because now the hydrogen and helium are burning in shells around it, and it becomes a supergiant again. So it does this whole dance all over again. Notice how the size of the star is dependent upon what's happening down in the core. When the star grows in size, it grows in luminosity. And it's growing in luminosity because the energy output that must occur is getting very, very, very high in the core, because there's no new energy source. It's contracting under gravity. It's running out of fuel. The atoms and molecules, they're not even atoms, they're just ions. The nuclei have to move insanely fast in order to find other nuclei that they can fuse with, because they're running out of sources of things to hit. So therefore the temperature has to rise. When the temperature rising means that the particles are moving faster. And they have to move faster because they have to go farther in order to find something, in order to make the fusion. So that's kind of what's happening. So eventually the carbon-oxygen core continues to collapse. It gets smaller and smaller, and that releases more heat by gravitational collapse, because as you collapse a gas, it releases the heat, and eventually the core temperature exceeds 600 million Kelvin, and then the density is insanely large. It's about up to 150,000 grams per cubic centimeter, which is 1,000 times more dense than lead or gold. So a typical gram, a cubic centimeter of gold might weigh a kilogram. But this star, which is a gas, will weigh 150 kilograms per cubic centimeter. And it's still a gas. It's just really bizarre. It's not a solid, even though it's much more dense than lead and gold, 1,000 times more dense. Finally, we can get to the point where carbon fusion can occur. And then we get all sorts of reactions. Carbon burning is a new set of reactions that happen for much more massive stars that are much more massive than the sun. Carbon can slam into another carbon nucleus, and that forms magnesium. Neon can slam into helium, and oxygen can slam into two helium nuclei, and that builds up an oxygen neon magnesium core. Now, the oxygen neon magnesium core is also inert because it's not hot enough to fuse oxygen into anything heavier than that. And so carbon 12-12 fusion creates the products of magnesium, or neon and helium, or oxygen and helium. Those are its byproducts when carbon 12 smacks into another carbon 12. This doesn't release a lot of energy because, remember, it takes a lot of energy to make them initially, and each larger nucleus that you get gives off less and less energy. So you got to do more of it, and there's less of it to do. So you have to do more of it. There's less of it to use because now we're knocking together fewer objects because they're all combined together, and you get less energy out of it. So this can't last long. And so the reaction rate must be higher so that it can stay, so the star can stay aloft. So carbon burning can only last about 1,000 years before it runs it out. And that's roughly where Betelgeuse is now. We think that Betelgeuse will one day explode in a supernova, which I'll talk about later and next time, but it might be within the next 1,000 years or 10,000 years or a million years. So where Betelgeuse is now, it has an inert oxygen neon magnesium core. Very rapidly, there's a carbon burning shell happening fantastically quickly around it. Above that it's hot, and there's nothing in there except that. The helium then mixes through, and that creates helium burning in the shell around that, and whatever protons are left that are just on the boundaries of that burn and fuse hydrogen into helium. So the helium burning shell makes helium, which descends into the helium burning shell, which makes carbon, which descends into the carbon burning shell, which then carbon burning creates oxygen, neon, and magnesium, which descends below. And all above the supergiant envelope, it's very, very, very unstable below. It's puffing off its outer layers, just like we saw initially with Betelgeuse just puffing itself apart, because the interior is an extremely violent place. So carbon, oxygen, neon, magnesium core is about what stars between the masses of about 4 and 8 solar masses will ever do. That contracts and contracts and contracts. That core of oxygen, neon, and magnesium contracts, and that contraction releases even more heat, and that pops and creates those shell burning around it, which is incredibly unstable, which pushes the star apart and makes it froth. Now, these are the low-end masses of stars that will end up making what we call Cepheid variable stars. Cepheid variables run between about 5 and 20 solar masses, and Cepheid variables will become incredibly important when we study the Milky Way and we study how we can find the distances to the cosmos. So these are the progenitors, and this is the time of life where some of these massive stars become Cepheid variables, when they pass back and forth into the upper left area of the HR diagram above the main sequence. So these kinds of stars eject all their stuff, just like we saw Betelgeuse doing, and they leave a white dwarf behind, just like we saw with the sun in the previous thing. So a massive, super heavy-duty stellar wind coming off and leaving a core behind, a white dwarf core with a large planetary nebula. Much more massive than that, at least 8 times the mass of the sun. Then carbon burning can happen. The carbon burning evolution is insanely quickly. It'll happen less than 1,000 years, and the star's envelope has no time to respond to that. And there's a big thing that's going to happen really soon. However, there are incredible strong stellar winds that can be shown, that are evident from these massive stars, and they can erode the outer envelope, pushing it outward, making enormous bubbles and burbling appearance to the star. And Eta Carina, which is one of the great examples of such a massive star, a star much more massive than 8 times the mass of the Sun. I believe that Eta Carina is about 20 to 40 solar masses. And we see from this Hubble Space Telescope image of the nature of this particular star, which is Eta Carina, which is clearly undergoing some violent stuff. These bubbles demonstrate that the star is incredibly variable. It's puffing off its outer layers incredibly violently. And this can't last, of course. And so this star is in the course of dying, and very, very, very soon it will do something very catastrophic. And one that, when Eta Carina finally goes supernova, you will be able to read by it at night. So for much more massive stars, the oxygen neon magnesium core contracts and contracts, and by contraction it releases gravitational energy. Gravitational potential energy then heats it up to 1.5 billion Kelvin. I mean, how do you even get past what that is? Okay, I really can't give you a handle on what 1.5 billion Kelvin is like, but let's just say it's bloody hot. And the density is now about 10 billion grams per cubic centimeter, or 10,000 kilograms per cubic centimeter. These are extraordinarily rare conditions. Remember that massive stars, extremely massive stars, make up the most rare of all of the stars in the cosmos. So even though they're incredibly bright, they're quite rare, with far fewer than 1% of the stars in the sky will ever do this. So neon, I'm not going to really go through all the reaction rates because now they get extraordinarily complex. And when neon burning occurs, it will create more oxygen, more magnesium, and lots and lots and lots of other heavy elements. Now we're below the element iron. Now, a lot of these reaction networks, remember the carbon, nitrogen, oxygen created neutrinos, as well as all of the carbon burning that created the oxygen, neon, magnesium. That created enormous numbers of neutrinos, and now most of the luminosity of the star becomes in neutrinos itself. And the star rapidly creates this core, and neon burning can only last a couple of years before it runs out. This temperature is simply too high, the density is too high, but neon does not provide, it provides even less energy than the previous step. And so there's fewer particles, it provides even less, the temperature is even higher, so the reaction rate is even faster. Neon is done in a couple of years. When you're done with that, well, what the heck? What's next? Well, you burn oxygen. Oxygen then starts fusing, and the temperature rises rapidly into about 2 billion Kelvin, and the density rises even higher in the core. Remember, this is still a gas. This is still a gas, and it's still gaseous because the temperature is so high, even though it's 20 or 30,000 times more, 10 or 20 million times more dense than water, and 10 or 20,000 times more dense than lead or gold. But this temperature finally allows oxygen to be fused into silicon, sulfur, phosphorus, and pretty much everything up until iron. Now, most of these reactions have enormous numbers of neutrinos because there's all sorts of, many of the reactions create huge numbers of neutrons, which then decay rapidly. These rapid decayed neutrons then get captured and also create neutrons as well. So there's multiple different reaction processes that are happening in the star. I'm not going to really talk about the S process or the fast process or slow process, the RRS processes, because that gets even more complicated. But suffice it to say that the star, in these last days, the neutrinos losses are much more, there's more energy coming out of neutrinos than there are in light. Now it's building up a silicon core. So silicon is now building up, and this lasts for about a year. Finally, oxygen runs out. the silicon core contracts and it heats up till it goes even higher in temperature and even denser, over 100 million times that of water, the density. And finally, when silicon burning occurs, the temperature is so incredibly hot that the silicon itself cannot withstand the intensity of the light that's there. The photons are so incredibly energetic at this temperature that they actually break the silicon apart into helium again and back down to protons and neutrons. So the silicon's getting destroyed by the light. And then the rest of the silicon is fusing into nickel and iron. That doesn't decay yet. This builds up an enormously heavy nickel and iron core, which will last only for about a day. So the temperature of the star, the luminosity of the star is incredibly large, but yet it only lasts a day. And here's nearly our finishing picture. At the end of this life of this supermassive star, more than 8 times the mass of the Sun, there's hydrogen-burning shells, helium, carbon, neon, oxygen, silicon, and all of these fusion shells where each layer is raining material down on top, from above, down below, as the pressure pushes it in. But yet, down in the core, there's an iron-nickel core, which is doing nothing. The size of the expanding envelope due to the instabilities happening down in the core is now bigger than the orbit of Jupiter, just like we see Betelgeuse being. And the reason for this iron-nickel problem is what we call the nuclear impasse. Now, why are we caring about this? This is what's going to happen. This is why there's a big, 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 big problem. When you fuse light elements together, you release energy. You release energy in the form of light, and you release energy in the form of neutrinos. But iron is the most tightly bound of those things. So you get energy by fusing light elements into heavier elements, so long as the elements are lighter than, have an atomic number less than 56, which is iron. So they release energy. But if you want to fuse elements heavier than iron, it must absorb energy. So once an iron core forms, there are no fusion reactions left for the star to tap in order to release energy. So gravity's still working, and that's what's happening. And here's a view of that thing again. Below iron, fusion will give off energy. Above iron, fusion takes energy, or more specifically, fission gives off energy. So that's why we use uranium in order to power our nuclear power plants, because uranium falls apart. And as it falls apart radioactively, it gives off energy. And that's what the far right-hand side shows. But we're talking about stars, we're talking about massive stars, and they all try to go towards iron, because iron is the most bound of all the nuclei. And if we look and zoom in really close to this binding energy, we find that it's specifically iron 56 and nickel 56, which are the most bound nuclei of all. And we see that this reaction network shows how much energy you get out, with the largest jump in energy coming from hydrogen up on the far left-hand side. When you start with hydrogen fusing to helium, that's the biggest step. When you fuse helium into carbon, notice the step from helium-4 to carbon-12 is really tiny. And then the step from carbon-12 to oxygen-16 is small too, but is much smaller. Again, from oxygen to neon, it's a teenier step. And so each step is smaller and smaller and smaller until you get to iron. So each step of this fusion reactions gives off less and less and less energy as it goes, until you get to iron, and then it takes energy in order to fuse it, because that's what the curve means. So that's the end of the road. At the end of the silicon burning day, there's just an inert iron core with some nickel in there too, and there's this huge onion skin of burning shells all around it. And very soon, the iron core exceeds about 1 to 2 solar masses and begins to contract and heat up. And what it does at the end is final, catastrophic, and amazingly bizarre and wild. That's the end of the road for these stars, and stars between masses between 4 and 8 times the mass of the Sun, they burn all the way up to carbon. And anything less than 4 solar masses only burns helium, and the cores of these intermediate mass stars become white dwarfs. Anything bigger than 8 solar masses gets all the way up to iron and does a catastrophic collapse. And what happens then, we'll talk about next time. Today we're going to be talking about supernova. And supernovae are exploding stars, supermassive stars that are at the end of their life, and they go out with a bang. So let's see how they work, because we talked about large stars and how they lived last time, and we found that they actually don't live as long a lifespan as low mass stars. So let's see what the big boys do. So the endpoints of various stars of solar mass levels is kind of summarized here. This comes from one of the Paterson type textbooks. And if it's really small, less than 8% the mass of the sun, it does not do anything dramatic. It becomes, they're brown dwarfs. And they basically do not, they never initiate hydrogen fusion. Between about 8% of the mass of the sun, about a quarter of the mass of the sun, the final end state would be a star that has completely converted itself from hydrogen into helium, and it becomes a helium white dwarf. Somewhere between, say, about a quarter of the mass of the sun and about 4 to 8 times the mass of the sun, this table I think is a little bit old, the star ends up as a white dwarf, a carbon-oxygen white dwarf. And if it's much, much larger, then about 4 to 8 times the mass of the sun, about 12 times the mass of the sun, at the time of main sequence burning, then it'll end up with a neon oxygen white dwarf. And if it's larger than that, with 12 solar masses, you get a supernova. And a supernova doesn't produce a planetary nebula or a white dwarf. It produces something completely different. So let's see what that looks like. Last time we talked about the last days of a supermassive star, and where we ended it with, where massive stars go through these in huge, fast burning. Burning now means fusing hydrogen into helium or some element into another element to liberate energy. And very massive stars, roughly at least 8 to 10 times, at least 10 times the mass of the sun, they burn hydrogen into helium for only about 10 million years, a very short time period compared to the sun's 10 billion year rough lifespan, which is about 1,000 times longer. And once they do that, they only burn helium for about 1 million years, convert carbon into oxygen and neon for only 1,000 years, fuse neon into oxygen for only about 10 years, oxygen into silicon only for about a year, and then the final stage of burning silicon into nickel and iron only lasts a day. Now this means that down in the core of this nested onion skin sort of thing, way down in the core, a very, very large inert iron and nickel core is building up rapidly and compressing and starting to do a major compression, as it's not producing any energies, but it does release energy by compressing. So it's releasing some of its heat by simply releasing it through gravitational compression. And that's what the iron core is doing. So at the end of this day, there's all of this shell burning, and we've seen burning again here means fusion. Hydrogen fusion, helium fusion, carbon, neon, oxygen, silicon, and fusion all the way down into the core. The exterior of the star is now extraordinarily massive. It's a red supergiant or a red giant or maybe even a blue supergiant, but it's definitely a supergiant star. And the size of the star now has expanded out to about 5 astronomical units, or almost the orbit of Jupiter or larger. But the core is extraordinarily compact, and that's where all the action is. The outer envelope is just primarily hydrogen and helium, but there's practically no mixing between the outer envelope and the inner core. So we're going to really, now we have a touchstone that we have to actually understand for what's going to happen next. And what we've really been talking about the entire time is how much energy is liberated by combining nuclei together. And that's what we call the binding energy per nucleon. And this graph, which comes from data that I downloaded from the International Nuclear Structure and Decay Data Network, which is a subdivision of the International Atomic Energy Agency, which governs, which tries to help people not explode nuclear weapons in various countries and so forth. That's one of the things they do. Anyway, they do have a very fascinating set of data about the nature of atomic energy and nuclear energy. And so I downloaded all the data and found how the binding energy per nucleon is in mega electron volts, which is a little tiny amount of energy, but in terms of nuclei, it's pretty large. The number of nucleons on the bottom shows how many protons and neutrons there are in the nucleus. So those were the nucleons we're talking about, protons and neutrons. And notice the graph has a peak right around 50 or 60, right? Just north of 55 or 60. And there's some other residual peaks off to the right, and there's a big drop off to the left. Everything that we've been talking about with those little stars up to this main sequence stars takes tiny nuclei, which would be on the lower left with a number of nucleons. 1 is hydrogen, which is a proton, and the number of nucleons builds from 1 up to 4. And in fact, I'm just going to move my mouse across and show you where helium is. And right there, where I put my helium, where I put this on there, that is helium. Helium nuclei are incredibly well bound. So if you put helium to get hydrogen together to helium, you get a big jump. So there's an enormous, enormous jump that happens when you bind hydrogen into helium. All right, so this graph shows how much energy is liberated when you put all these protons and neutrons that into a nucleus, or how much energy you have to provide to the nucleus to tear them apart. So it's interesting to note that this graph has a peak, and it drops off to the right for very, very large nuclei, and it drops off to the left for very small nuclei. So this means that we will have what's called a nuclear impasse. The fusion of light in elements, anything less than iron, gives off energy due to fusion. So we see in this graph below that hydrogen, or H1, which is just a proton, gives off energy by fusing hydrogen to deuterium, H2, which we see down below. And that's what we've known that, though, since we talked about the proton-proton chain. And we also knew that hydrogen fusing to helium gives off a lot of energy, because there you see He4 in this graph, and that gives off energy. We also know that fusing helium into carbon gives off energy, but not as much. See the difference in energy between helium-4 and carbon-12? It's not as much as the difference between hydrogen-1 and helium-4. There's a large amount of energy that's given off by fusing hydrogen-helium, but not as much from helium to carbon, and the step is even smaller from carbon to oxygen. In fact, if you look, you can see that as you go up and up and up to the peak at iron 56, that each step is progressively smaller. You get less and less and less energy out of the reaction by combining something with carbon-12, combining it with a helium nucleus to form oxygen-16. You don't get as much energy. In fact, the energy difference to get it from oxygen-16 to iron 56 is very small. So therefore, there's less. This is what we were talking about in the last time, is as it progresses, each successive step provides less and less and less energy output. It also takes more energy to do it, because these things have protons, and the protons push against each other for the electrostatic force. And so you get less and less energy out. The nuclei are bound less and less strongly, which means it takes less and less energy in order to rip them apart. And if you fuse but the general trend of this whole graph is that if you fuse elements lighter than iron together, you do get energy out. And if you have and to get elements heavier or more massive than iron, with more nucleons in the nucleus of the nucleus, then it actually has less bound. So if you look at uranium-238, we have the cross there, we have on the right-hand side, we see that it is less bound than iron-56, meaning it has less binding energy per nucleon. And so just piling stuff on top of it it means it takes energy to put these things together in order to actually create uranium-238. You don't liberate energy, you absorb energy in order to go there. So here it is again in larger form. We see that helium to carbon gives off energy because you go up. Carbon to oxygen gives energy because you go up. And oxygen all the way up to neon, and magnesium all the way up to nickel gives energy all the way up to iron 56. And below that, fusion gives off energy. But if you fuse elements together and try to go more massive than iron, it takes energy, because the binding energy is less, so you have to push it together to keep it together. That's a better way of talking about it. In fact, another way to look at it is we use uranium in our fission nuclear reactors in order to get electric power, and we get that power by uranium radioactively decaying down to lead, and that gives off energy. And so uranium decaying to lead, which is about halfway up, or more than halfway up that from the far right-hand side to the left, towards the peak, gives off energy. So above iron, fission gives off energy, and to get things more massive than iron, it takes energy. All right, so this is a more detailed view. And I was poking around on the internet to try to find a little better view, but this is not very clear. And what I did then is I decided to try to zoom in and show you what's really there, but it's really not clear. We've got iron 56 and nickel 58 at the top. We have strontium 6088 and scandium and cesium, and there's polonium, lead 208 way down there. But these graphs are kind of hard to read. I'll grant that because they're low resolution on the internet. So again, I went back to the IAEA website and grabbed just that data to see what the most bound nuclei are. And we'll look at the top peak. We see there's three nuclei that are the most bound. And iron 56 is the leftmost of the three top ones. Nickel 58 is just a little bit more bound, and then there's nickel 62, which is also just a little bit more bound than nickel 58. So what you find then, but nickel 58 is, I believe, is radioactive, so it's going to decay. And nickel 62 is also radioactive, so it will decay. And they'll decay rather rapidly. So even though they have a high binding energy, they're also radioactive, so they fall apart. In any event, and also they take a lot more energy, and conditions tend to not be correct for them to actually stay together. So you have to have very different conditions, and we're going to see what those conditions are in the center of a star, because iron 56 is the most common element in the universe for a reason, and it's at the top of this peak. So anything below this peak, you get energy by fusing things from the left-hand side of the peak up to the right-hand side of the peak. And the typical fusion means take an element, take a nucleus, and either slam a proton into it or slam a helium nucleus into it. That tends to be the dominant reaction that you would do in order to do fusion. You sometimes have like two carbon nuclei slamming together, and that falls apart and gives off stuff. But it's very easy to say, let's get a helium nucleus because it's lighter than a carbon nucleus, and spin it up really fast so they can smack into stuff. Be that as it may, however many ways there can be, because each one of these dots is a separate nucleus. So there's lots of different nuclei, lots of different isotopes of various nuclei. But you get them by doing fusion or then radioactive decay by fission. All right, so what happens in the center of a star? In the center of the supermassive star, the iron core is going to grow and grow until by the silicon fusion happening above it, until the mass becomes about somewhere between 1.2 and 1.4 solar masses. And then the core will collapse under its own mass because it exceeds the Chandrasekhar limit for it exceeds the limit that a white dwarf can have before it will explode. So a white dwarf is basically forming an electron degenerate core in there. It can't be supported by electron degeneracy, and all of a sudden the core collapses down rapidly and heats up amazingly. And it gets up to about 10 billion Kelvin, and the density is about 10 billion grams per cubic centimeter. So one sugar cube would weigh 10 million kilograms, or that roughly translates into a few 100,000 tons. So we have a sugar cube weighing hundreds of thousands of tons. That's a lot of weight, and that's how dense the core becomes. However, even though it's that dense, it is still a gas because it is so incredibly hot. And way down in the center, it's incredibly turbulent because the star's core is rotating, and as it rotates, it spins everything around, and so you got this crazy mixing happening. And even though the core is there, it's not moving. It's the star itself is spinning. Now, when it's that hot, the energy is primarily in the form of kinetic energy of the nuclei bouncing into each other, and that's at roughly the same temperature as the light. So there are gamma ray photons that can't go very far because the density is so incredibly high that they actually equalize the temperature with the material around them. So everything is the same temperature, both the light, the profile of the light in the black body spectrum, as well as the nuclei that are zipping around. And that has a number of results. Once you get enough of the energy in the form of light, then the light itself has enough energy in form of a number of mega electron volts to actually disintegrate the nuclei. Remember, those nuclei have binding energies of iron is roughly about 8 or 8.5 or 9 mega electron volts. And once the temperature of the center of the area exceeds about 10 billion Kelvin, which is really high, that's 10 billion, right? 10 billion. Once it exceeds that, then a significant fraction of the energy of the light actually has an energy on the order of about 10 or so mega electron volts, which is a very high energy gamma ray. So once these gamma rays go flying around, they can actually disintegrate the iron nuclei. And when the iron nuclei disintegrate, they absorb the energy of the light. And then that lifts the nucleus apart, giving the constituents its energy. And that binding energy then is absorbed out of the system. And so as the nuclei now start to absorb the light and then break apart because of it, this is called photodisintegration, it removes the light and therefore removes the energy that supports it. It robs the core of energy. It robs the core of pressure because if it's hot, it has high pressure. Second, then the density continues to increase, and at this, because as everything's breaking apart, then you have free neutrons and free protons. So as there's photodisintegration happening, it doesn't just break it into helium nuclei, it breaks it down into also protons and neutrons. That's very high energy light. And so now the protons and electrons are very close together. They can fuse together to form neutrons. And the neutrons then, of course, give off neutrinos. And neutrinos carry a tiny amount of energy, and as they carry a tiny amount of energy, they escape, and they just leave. Because neutrinos don't see anything. Remember we talked about the surface of the sun, deep, deep, deep in the core of the sun, where neutrinos just escape. The reactions occur in the sun, and they don't even see anything. So the neutrinos get out of there, taking energy further away from the core, leaving it with no energy. So there's no energy to provide pressure against gravity, because remember, gravity is always working. So the neutrinos escape, carrying away more energy to provide the pressure, and then it collapses catastrophically. So right around this only lasts about a day, this whole event. And once the iron core starts to collapse, it begins at about something roughly the size of the Earth, at a density of and the iron core collapses at about 100 million grams per cubic centimeter. And then a second later, this is almost free, it's faster than free fall. Actually, it is free fall given the gravitational pull that it is. In total free fall, it drops from 6,000 kilometers in size down to 50 kilometers in size in less than a second, at about a quarter of a second later. And then the density increases to almost 10 to the 14th grams per cubic centimeter, which is astonishingly high density, and that density is the same density as an atomic nucleus. So you can't really push the nuclei together anymore because now they're literally in contact. So the density raises in the core, and it has to stop because now neutron degeneracy comes into play, just like we talked about electron degeneracy in the center of the sun. That causes the helium flash in low-mass stars. But with neutron degeneracy, that then says, I'm a neutron, I can't go on top of another neutron, I can't go inside another neutron, we can be right together, we can be next to each other, we can touch each other, but we can't be inside each other. So therefore, the neutrons don't have any place to go except stack up against each other, and they cannot compress anymore. So since they cannot compress, basically it makes a bounce. So then you have an enormous bounce off the core because material still is piling down on top of it. The core is now collapsing down to about 2.5 times 10 to the 14th grams per cubic centimeter, which is the density of an atomic nucleus. And the strong nuclear force now comes into play, which does all sorts of weird things. Strong nuclear force is really poorly understood. But what it does is it actually says that now you have gluons that are doing the interaction between the protons and neutrons, and that interaction is very powerful and keeps the nuclei from going on top of each other. So the inner 3/4 solar mass of the core, that just stops. So everything else starts to fall on top of it, and it springs back a bit, doing what's called a bounce. And so material still keeps falling on top of it, but now that core collapse is coming back up. And that creates a shock wave. That shock wave kicks out about a huge amount of energy, 10 to the 44th joules, which is the equivalent of about 100 billion suns. That all happens in less than a quarter of a second. And in about 20 to 40 milliseconds, which is the same time it takes you to snap your fingers, all the matter that is getting swept up by the shock wave there's a bunch of stuff that's falling down on top, and the shock wave's coming up, and it stalls, because now you've got material coming up and material coming down. You've got a shock wave above it, and then the interior of the core, because protons and electrons are still becoming neutrons inside of that core as part of this compression. The neutrinos are still trying to get out, and they can't, so they basically get trapped. Finally, it becomes dense enough for neutrinos to get trapped. And by trapped, I mean 1 out of every billion or so. The other 999 million get out. But 1 in a billion, considering how many neutrinos are coming out, that's enough to do it. Those neutrinos get trapped in the gas. They then heat the gas, depositing their energy through weak nuclear reactions inside of the gas. And that turns it, because it's uneven across there, because neutrino interactions are rare, so it's going to be an uneven sort of distribution. That leads to incredibly violent convection right above the core, which is trying to bubble away and turn itself into one big atomic nucleus. And that makes a new shock wave as the neutrinos now push the whole thing apart. About 300 milliseconds, which is just over a quarter of a second, which is also, interestingly enough, that's about as fast as your brain processes thoughts, 300 milliseconds. That's interesting to think. So as fast as your brain can process a thought, the shock wave reappears and smashes out through the star, pushing up against the infalling matter, creating massive amounts of nuclear fusion in the wake because of the high density and high temperature. That shock that comes back up, which is now a shock wave or an explosion wave, heats and accelerates the rest of the star, and the shock eventually breaks out through the surface, moving at almost 10% of the speed of light. And from a distance, we see a star that's now about the size of Jupiter's orbit explode. And that's what we call a supernova. And for a very, very brief time, within minutes, a supernova can outlast up to 1 to 10 billion times the luminosity of the sun for just a few minutes, and in fact much longer, and it can outlast an entire galaxy of stars in terms of its output of light. And the outer envelope is then blown off into space along with much of the core and accelerated to a fraction of the speed of light. Remember, the speed of light is 300,000 kilometers per second. So this is going 1/30th of the speed of light. That's pretty fast. And that's a really fast shock wave. It's not a pretty thing. If you were next to it, you'd be dead. It doesn't matter how close you are, you'd be dead. You can't be Superman, you'd be dead. If you were within a light year, you'd be dead. That's just how this all works out. And, well, you're not going to be there, and they're never going to do an episode of Star Trek, and I'm even sure Doctor Who would lose it on that one. Anyway, the gas will expand, eventually cooling off, leaving only the core behind. And we see in the background here a galaxy that has a supernova in it. We see the supernova on the outskirts of this galaxy. And notice how it's almost as bright as the core of the galaxy. This is a dimmer supernova, but it was seen around that galaxy. In fact, you could think it might even be brighter than the core. And remember, the core of the galaxy is composed of maybe tens of billions of stars itself. So one star is much brighter than maybe tens of billions, 50 billion stars that are deep in the core of this galaxy for just a few months. And that's what a supernova is. And this has a name, 1994D, because it was seen in 1994, and it was the fourth one observed in 1994. So that's why it's called Supernova 1994D. Then this was one that I saw in 2014. This happened in the nearby galaxy M82. It was a different kind of supernova, but still the point's the same. It was a super bright star, and that bright star appears inside of the disk of the galaxy. Don't look at the star that's right above the number, the magnitude label. Look inside the disk, and you'll see that there is one star that's actually getting brighter and brighter with time, and then fading with time. And so we see that as time goes on, this particular star is getting brighter and brighter and brighter and then fading. So the order of the images is upper right, middle right, lower right, upper left, middle left, lower left, which is kind of a weird organization for it. But what the heck, somebody was reading it that way. That's good for them. I forget why this image came about like that. But we definitely see the star getting brighter as time goes on. And that was in January of 2014. And I remember taking out a telescope into the park in New York and actually going outside and seeing this supernova inside of that galaxy. I had a 15-inch scope at the time. And when I looked at that thing, I could definitely see a line of 3 stars. I could see the 2 stars, and it's most obvious in the lower left-hand corner of this image, as well as the core of that galaxy. So this was eminently within the observational capacity of a 15-inch telescope in an urban environment. I saw it. And there's another image. This was taken by a micro-observatory, and we see all the way over on the right, and I'll just use my mouse to kind of point over to it. There it is right there. There's the supernova in M82. Here's another supernova in the galaxy NGC 1309, and there's a Hubble follow-up image with respect to it. The left-hand one, taken by the Lick Observatory, was in 2002. And once you run out of letters, you start doing 2 letters. So they went through the entire alphabet, and that's because F and K. What does F and K mean? Well, there's been, since 1994, serious supernova studies, so people are able to find large numbers of supernova by going and hunting for them. So dedicated supernova searches have found hundreds a year. And we see in the Hubble image from 2005, they're able to pinpoint exactly where that star was in the sky and try to look for remnants. And there's one that happened in 2005 in the nearby galaxy M51, which is the Whirlpool Nebula. And there's that galaxy we saw in 1994. And finally, let's look at the nature of what a supernova explosion kind of looks like. They're very, very, very luminous, and we talk about light curves. And that's why we have these images that we looked at before, is that how does the luminosity of such a star change with time? And there's 2 types, 2 general types. There are many, many, many sub-classifications. But I'm just going to keep it with these 2 types because it makes it a little easier to understand, because there's 2 principal versions of supernovae. And we're really only talking about one kind this time, which is called core collapse supernovae. And a core collapse supernovae is called a Type II supernova, and that's the green line in the background. What you see is that there's an incredible brightening, and then it dims for a while, and then it has a plateau, a flat plateau for a while, where it stays at roughly the same brightness for a long time, maybe a month or so, and then dims again at kind of a curve, and then the curve changes shape again. Each one of those changes of curvature is a result of different material glowing. So the initial brilliance of the supernova will fade over time, and it's slow because all of the gamma rays, remember that supernova explosion had all sorts of things mixing down right above the core. And that means there was a huge amount of nuclear fusion that occurred explosively in the core, and rather rapidly. So in that explosion, it created large numbers of radioactive elements, and this primarily radioactive nickel and radioactive cobalt. And the 2 curves actually we see that there is a decay of radioactive nickel to cobalt to gamma rays. Those gamma rays then illuminate the gas that surrounds the supernova and makes it glow, because the gas might be too thick to actually let the gamma rays come straight out. But then the gamma rays themselves glow. The gas itself glows because it's been heated by the radioactive decay of nickel and cobalt. And so that's how we have these kind of plateaus and peaks as the radioactive decay. Those peaks then plateau, and then peak, and then decay. And that's all because of the radioactive decay of those other things. Nickel tends to be the thing that fades out more slowly at the top, and cobalt is primarily responsible on the right. So there are also these 2 types of supernovae, not just their light curves, meaning one just gets bright and then slowly dims, that's the Type Is. The Type IIs have a slightly different appearance to them. Type Is have no hydrogen line emission features, but Type IIs do. And that makes sense that a Type II supernova would have a lot of hydrogen line emission. Remember, hot hydrogen gas happens because it gets really hot, right? And so the atom gets ionized or excited and drops back down from excited states down through. So you get hydrogen emission lines in visible light. And so you should see that pinkish glow of hydrogen, or at least an emission line looking at the spectrum. That's because the outer 5 astronomical units of the star, or a significant fraction of the star, did not participate in the fusion down in the core. So it's still hydrogen. So Type II supernovae have hydrogen emission lines, but strangely enough, Type I's don't. So core collapse supernovae are the Type IIs. They do have significant hydrogen absorption lines, but Type I's don't, which is really interesting. So let's look at one in particular. One of the more recent ones that came out that happened when I just got done with high school. So when I was in high school in 1986, I graduated and went off to college and started studying astronomy, and everybody all of a sudden started talking about Supernova 1987A, the first one in 1987, in February 23rd. And that happened in the Large Magellanic Cloud, and the Large Magellanic Cloud is a neighboring galaxy to the Milky Way. It orbits at about 160,000 light years away. So for a very short period of time, it was brighter than 5 billion suns, which is amazing. Finally, which made this really important, we haven't had many Milky Way-based supernovae. Now, the Large Magellanic Cloud is not part of the Milky Way, and the Large Magellanic Cloud is outside the Milky Way, but we haven't seen many naked-eye supernova since Kepler saw one in 1604. So this is the picture that was taken by the Anglo-Australian Observatory of Supernova 1987A. The right-hand side shows before, and since it's in the Large Magellanic Cloud, and that's a close-by galaxy, this is an extraordinarily studied area. And because it's so well studied, there's lots of pictures, and people were able to determine exactly which star it was before it exploded. And there's the star. And we can see there's the Large Magellanic Cloud itself in the sky. It's a star-forming region. It's a huge star factory. And from then we take a slightly different view of it from an emission line survey on the left-hand side, and then we show where this location is in Supernova in the Anglo-Australian Observatory's image of it, and then we see a Hubble Space Telescope image of it being close up. And this was a star that exploded that had 20 solar masses. So here's some of the vital statistics for 1987A, which was a supermassive star. It has a funny name named after the guy who actually made a catalog of these large stars, these hot stars in that area. Large Magellanic Cloud, distance about 50,000 parsecs. And the type of star was a B-type star, a B-type supergiant. So it's not as hot as an O star, but it definitely is a hot blue star. And the size of the star before it exploded was about 50 times the radius of the sun. The surface temperature was about 16,000 Kelvin. Remember, the sun is 6,000 Kelvin. So the surface temperature was just only a little bit hotter, only 3 times hotter than the surface of the sun. However, the core was a different matter. The luminosity of that star prior to its explosion was over 100,000 times the luminosity of the sun, and its mass was about 16 times the mass of the sun. Now, there was another really interesting thing that happened at this exact time that the star went off. A neutrino burst was detected. At that time, there were a number of neutrino observatories, and 3 of them actually detected it. And there were 19 anti-electron neutrinos detected by the various neutrino observatories across the world. The Kamiokande Observatory, which is in Japan, observed 12 of those 19. And the energies of these neutrinos were about 20 mega-electron volts. Remember, the binding energy of the core of a nucleus is about 8 or 9 for iron nuclei. So these neutrinos were given almost 3 times the energy required in order to rip apart an atomic nucleus of iron, which is fascinating. So there was a huge amount of energy being pushed into neutrinos as the star was collapsing in the core. The thing that made it really interesting and this star began the process of what's called neutrino astronomy, because they were detected 3 hours prior to the light of the star. The star was observed by an astronomer because it was up at night, and it was seen in the sky at night. And he reported it the time he saw it, and he swung a small telescope over to take a picture of it when it was observing down in Australia. I forget the name of the person, but under the 1987A website, you can certainly find it. On Wikipedia, you can certainly find out about it. But because the distance to it is 168 1,000 light years, and because we detected 19 antineutrinos across the Earth, that meant because of how seldom and how rarely neutrinos interact with normal matter, there had to be 50 billion neutrinos coming from supernova 1987A, arriving at Earth, at the Earth's distance from it, 168,000 light years away, 50 billion neutrinos per square centimeter. So hold out your thumbnail, that's about a square centimeter, and at that moment 50 billion neutrinos passed through your thumb at that point from that one supernova. That meant the total number of neutrinos that was emitted from this explosion was about 10 to the 58th. That's a big amount of neutrinos. That's a 1 with 58 zeros after it. I mean, I didn't even bother to write it out because, I mean, it'd be cute and everything, but who wants to do that on this thing? And the neutrino burst lasted about 10 seconds, which lends credence to the idea that the neutrinos get all bunched up. And there were actually 2 or 3 waves of neutrinos that occurred. The total energy released in the neutrinos is about 10 to the 48th joules, which is about 10 to the, if you add it up over 10 seconds, that's 10 to the 22nd times the luminosity of the sun. That's a lot of energy. In fact, 99%, more than 99% of all of the energy of supernova 1987A and all core collapse supernovae go out in the form of neutrinos. Neutrinos carry away almost all the energy. Sure, we can see it as a bright thing. But if we could look in if we had neutrino detecting eyes, we would be blinded because there would be too many neutrinos for us to see. And the luminosity of it was astonishing in terms of how much luminosity there was in energy compared to the sun. So the peak visible luminosity, meaning how much light it emitted, was about only a measly 4 times 10 to the 33rd joules, which is only about 10 million solar luminosities, which isn't much. So that's incredibly small compared to the neutrino luminosity. It's a tiny fraction. Remember, you subtract, that's about 10 to the 15th times less luminosity in light than there was in neutrinos. Well, the material that got ejected really hard at 10 to the 7th meters per second. That's about 3% the speed of light. And about 4 solar masses of material got ejected from this supernova. And it imparted 10 to the 44th joules of energy. So the kinetic energy of the material is comparable, or at least it begins to be comparable, to the total energy released in neutrinos. So the kinetic energy is about 1/100th of 1% of the neutrino energy. And just to give it a reference frame, it became as bright as a 3 magnitude star. So it was pretty bright. So if you were down there, you could say, hey, what's that new star in the sky? Because a 3rd magnitude sky under dark sky conditions, and if you know your night sky, you'd say, that's a new star. You would have noticed it. It is a distinctly noticeable star. It wasn't as bright as like -2, like Venus or something, but it was as bright as one of the stars in one of the belt stars in Orion. That's as bright as that. Or one of the brighter stars in bright constellations, such as those in the Big Dipper. So it became pretty bright. It was definitely a naked eye star. But remember, most of the energy was not in light, wasn't even in ejected material. Almost all of it was in the neutrinos. However, that doesn't stop people from looking at stuff. And what's really neat is the American Association of Variable Star Observers had a number of people who took a look. And what we see is this is the light curve from visual observations of supernova 1987A. And this is in the V magnitude, and we see people making magnitude measurements over the course of time. And this can be downloaded from the avso.org, and it shows that it was caught before the peak occurred, then the peak occurred, and then it had a plateauish sort of long slope, and then it had another drop-off. So the first peak, when it was observed, was the initial explosion, and then it got brighter as time went on because nickel-56, which is radioactive, decays to cobalt-56, and which is also radioactive. So the nickel has a very short half-life, and that's the first decay of the curve, and it got brighter because that stuff was seen. As the shroud of gas was revealed, it got brighter and brighter and brighter. So the first slope down is the dimming as the nickel 56 finally decays and becomes cobalt 56. Then that drops away. There's not much nickel 56 left. We got a bunch of cobalt 56, and so we got this longer, slow, slanted curve, and that shows it decaying to normal iron 56. So iron 56 is the most common thing in the universe because everything more massive than it, or at least many of the products that would be formed in supernovae, decay to iron 56. And then it kind of has a nice little curve at the bottom, and that's just the remaining gas and dust being heated by X-ray emission from residual things as well as shock heating from around. And it got dimmer and dimmer and dimmer. And once it got below magnitude 6, it was below naked eye view, and then people were using telescopic views all the time. So that's really interesting. And we see how long it takes for these things to go, and you can see that it was observed in February, and it was a big burst of observations right there, as people ran to their telescopes in order to make these strong observations. And if you went to the AAVSO website, you'd see how many people actually participated, which is a lot. So later on, we see images of rings surrounding supernova 1987A, and the bar shows the angular diameter of the moon, which is 1/60th of the angular diameter of the moon, which is about one half of an arc minute. So that shows it's not very big in the sky, but at least it's noticeable in a small telescope. So when this was looked at, it was determined by subsequent Hubble observations that this glowing ring exists. These rings, that really bright ring in the center, has been there for about 20,000 years before the star exploded. And when the X-rays from this explosion energized all the gas, it's making it glow. And all these things, these blobs, are moving really fast. That blobby structure is moving at about 20 million miles an hour, and that creates a shock wave of material that slams into, and that shock wave of material heats it up and makes the material in the surrounding medium, the surrounding interstellar medium, glow. So there's the glowing material moving at millions, at tens of millions of miles an hour, slamming into the interstellar medium and causing it to be hot and emit X-rays. And there's also these kind of interesting bubble shells as well, which are like light echoes. And we can see that the Hubble Space Telescope imagery from 1994 to 2003 shows the evolution of this ring. The initial ring was heated by X-ray emission, and then as time went on, the material from the supernova slammed into that hot ring and made it glow brighter. And there we see a detail. There we see a brighter detail showing the knots of hot gas that's been heated to extraordinarily hot, maybe tens of millions of degrees. It also emits X-rays. And how did this actually come about? What's different about this? And we're going to go into this a little bit later too, but let's look at how supernova 1987A might have arisen and where those rings came from. Probably the star was a binary system, and the more massive star evolved first, became a red giant, and as it became a giant, it literally engulfed its close companions. So these two were incredibly close stars, and then the two stars, one star got larger and larger, and that provided drag on the other star. Third, the two stars, in so spinning, most of the star, the red giant, got pushed out into a spinny envelope to conserve angular momentum as one part merged and the other part expanded away. So then you have this ring that's been expanding away as the two stars now merge together into one. Then as they merge, you have basically something that's very similar to a protoplanetary disk like we saw in the interstellar medium stuff. And that's what the bipolar outflows of gas made this ring-like structure in the bubbles above. Finally, then, there's a massive explosion that occurs, and that's the supernova that we saw, all in bright light. And then the ejecta start to move outward, and once the ejecta then from the supernova slams into the disk, it makes it glow and forms those beads. So there's the story of how people think it actually worked. And so you have all these knots of gas and dust. There's bipolar flows, meaning that's what that inner glow is about, from the jets that occurred from the supernova as the material flows outwards. So there's some hot material sitting there. And yet, this should have formed some sort of neutron star or black hole, but it isn't seen yet, and it basically has not been revealed yet because the gas density might be too high. There's no reason to think that it's not there yet. It's just hidden for some reason. Maybe it got ejected and shot out to the left or something like that and left the entire area, but there should be some kind of disruption if it did that. And angular momentum would say that it would probably be shooting off into the ring structure around it. Anyway, we see that there's a pretty interesting explanation for those fun ring structures of supernova 1987A, which was the nearest supernova to us since 1604. And why we care about supernovae, and we're getting close to the end here, so bear with me, is because nucleosynthesis is where we get all of the elements in the cosmos. We start the universe with hydrogen and helium. The Big Bang made hydrogen and helium, but stars make everything else. They fuse hydrogen into the light elements up to iron and nickel, and they come in layers, and when a supernova explosion comes out, that releases nuclear fusion of the light elements up to iron and nickel. That explosive fusion does. And then there's all sorts of neutron-based reactions because of the dense area inside of the supernova explosion itself, and also the radioactive decay in the supernova remnant that occurs and that creates all sorts of heavy elements up to 254 californium, which is 254 nucleons in it, which is really rich in neutrons. And those things then decay rapidly to other things like lead or iron. Supernova explosions create nearly all of the heavy elements in nature. That's where they come from. The iron that you use that is in your blood was formed in a star. The nickel that you pay pay a piece of candy for at the nickel and dime store, that was made in the center of a star. The universe started out with about 75% hydrogen and just under 25% helium and little bits of lithium, boron, and beryllium, but nothing else. Every other element were fused in nuclear reactions inside of stars, and all heavy elements above above iron are formed in supernova explosions of various kinds. So the 10 most abundant elements in the entire universe are hydrogen, helium, starting at the top, all the way down to sulfur and magnesium. And notice what's interesting about what we see in the topmost 10 abundant elements is that many of them, like magnesium, carbon, oxygen, nitrogen, iron, those things are really important for life. So the elements that make up life are incredibly common elements in the cosmos, and they're also small on the periodic table. We also see silicon being a very large amount that was formed, and notice what the Earth's crust is made out of mostly, primarily silicon oxides, and so that shows where planetary objects come from. So planets are made from silicon and iron predominantly, with all sorts of other stuff and carbon and oxygen, and life uses those common elements in huge amounts in order to metabolize and live. So what happens to that supernova remnant, such as 1987A? Well, you get all sorts of all the materials that were made in that, all the fusion-enriched stuff was made in the explosion. It expands at thousands of kilometers per second. That makes a blast wave. As we saw with 1987A, it plows into the interstellar medium. It stirs the interstellar medium. It makes an ionized nebula that can be seen for thousands of years. We'll talk about supernova remnants next time. But that makes something to be seen for a few thousand years after the explosion. And that material then mixes with the interstellar gas. That mixed gas becomes part of the next generation of stars with these metals, and then the next stars are more metal rich. And by metal, I don't mean like iron and nickel and so forth. I mean any other element heavier than helium. That's what astronomers call metals. That's a really funny thing. So metals are things that are heavier than helium, and all successive stars have more of it as a result of that. So the material that was formed in those supernovas goes out into space, and all of the things that are us, that were formed in some supernova long time ago in the same galaxy, and somewhere very nearby, because there would be stars but slightly less massive stars emit a huge amount of carbon and oxygen before they decay. There's a different kind of star, but the vast majority of all heavy elements come from supernovas such as these. And therefore, the solar system itself formed 5 billion years ago by gas that was enriched from these massive star explosions. And so stars form, they evolve, they live, and they die. And then they push out that stuff into the interstellar medium and make more stars. And that's what we mean by this thing that we saw earlier on, that this beginning stars start from clouds of gas and dust. They form protostars. They go through their main sequence lifespan. They then become red giants or explode as supernova. If they become red giants, they puff off their outer layers as planetary nebula. The more massive red stars, like a little bit more massive than the sun, churn out a lot of carbon before they do that. The most massive stars go into these core collapse supernovae and explode wildly in order to make these Type II Supernovae. Sometimes they'll form a neutron star, and sometimes they'll form a black hole. The most massive stars at the top of this thing can go straight to a black hole, and that's really interesting. And we'll talk about those when we talk about gamma ray bursts. But for now, notice the cloud on the left forms stars that are protostars, and stars become that way, and they shed their outer layers or explode or something like that, and seed the right-hand side of this, which is more and more and more gas and dust. And that then loops around to the left, with the small mass stars at the bottom and the high mass stars on the top, with 80% of all the stars in the Milky Way just brown dwarfs and red dwarfs, with the rarest of things, the tiniest sliver of stars become blue giants, blue supergiants, and explode violently in these ways to make supernovae. Today we're going to be finishing off our exploding, dying stars and the lives and deaths of stars with supernova remnants, some of the most beautiful objects in the sky to go look for with a telescope and to look for with telescopes that aren't your eyes, meaning something up in orbit or a Hubble Space Telescope or an X-rays or infrared or gamma rays or so forth, because supernova remnants emit huge amounts of light that is a very, very strange source of light, and unlike stars. So these are the bits from the dead stars that we saw last time when we looked at supernovae. All right, so let's review again what supernovae are. Supernovae come from extraordinarily large stars, stars more massive than, say, 5 to 8, roughly 10 times the mass of the sun, which are the top 3 rows, or more specifically, the second and third row from the top. And we see that there's 2 types of stars, blue supergiants that become Type II supernovae and become black holes, or it becomes a supergiant, a blue supergiant that becomes a Type II supernova and forms a neutron star. So these are the kinds of things that we're going to be looking at today. Okay, so remember again, stars that are really massive, above 10 times the mass of our sun, will end their lives catastrophically in a massive explosion that can be seen for many, many millions, if not billions of light years away, as they outshine their entire galaxy when they explode. And when they explode, they create all of the abundant elements in the universe. Anything bigger, more massive, meaning any element on the periodic table greater than iron, which is Fe on this thing. Fe is 26. Look at the 4th row right in the middle. Iron is Fe. And that's the heaviest, most bound element in the entire periodic table. But everything larger, below iron and to the right of iron and down from iron and higher atomic number than iron, was made in some sort of supernova. So these top 10 elements in terms of their most abundant, it's hydrogen, helium, oxygen, carbon, all the way down. Notice they're all less massive than iron. But all the important things for life, like carbon and oxygen and nitrogen and iron itself, hydrogen do because of water and acids and bases and all sorts of things that hydrogen provides, that's where they come from. So nucleosynthesis occurs in the largest stars. They all fuse hydrogen into helium as part of their main sequence lifetime. But when stars are much, much older or much, much bigger than the sun, 8 times the mass of the sun, they will convert light elements all the way up to iron and nickel, and then those accumulate in layers, and then there's an explosive fusion that happens that builds even more light elements up to iron and nickel, but that also sets up a huge number of reactions that inside of the explosion, where the densities are extraordinarily high inside the core of the star, as it's exploding, that create huge numbers of very heavy elements, all the way up to, say, californium, which is 254 atomic nucleons in its protons and neutrons inside of its nucleus. So these things get all created, the vast majority of which are radioactive, and then decay back down all the way down to iron. So the more massive things decay back down to iron, or find a stable nucleus that doesn't decay. And then we find that supernova explosions are literally responsible for creating every one of the heavy elements seen in nature, except for hydrogen and helium, which were formed in the Big Bang. So supernova remnants, these things are the exploded elements of the star, because most of the star gets blown apart when it explodes, when these massive stars explode. So of a 10 solar mass type star or a 20 solar mass type star, perhaps 10, if it's a 20 solar mass star, perhaps at least 10 solar masses gets exploded out into the cosmos as a result of the explosion, where some of it may fall back down to a neutron star or a black hole, but some of it was ejected as part of the latter portions of the star's life and forms a nebula around it. And if there is a nebula around it, then the supernova's light can slam into that nebula and illuminate it, like we saw with supernova 1987A. And that the blast wave then can plow into the interstellar gas, which is partly created by the supernova itself. And then it stirs and heats up the medium, and it makes it hot enough. And this kind of nebula lasts a couple thousand years for after the explosion. So this leads us to the concept of stardust. The metal enriched, and by metals we mean any element heavier than helium. That's what astronomers call metals. Metal enriched supernova, it mixes with the interstellar gas, that creates new stars, that becomes part of the new star mix, because stars are almost all hydrogen and helium. Remember, the oldest stars have very little of elements heavier than hydrogen and helium, but the very youngest stars, meaning stars formed within the last 5 to 10 billion years, do not have or have a significant enrichment of, say, carbon, nitrogen, oxygen, iron in their atmospheres because of the previous stars out of dust out of which they formed. And that's where the silicon and oxygen and carbon and everything that we know of that makes up the entire planet Earth was formed. It was formed inside of a star that exploded maybe 5 to 10 billion years ago. And the material then floated around the galaxy, floated on the Milky Way, until it combined with another interstellar cloud. That interstellar cloud collapsed, as we saw, just like the interstellar medium and star formation in previous lectures, that it collapses down and forms other stars. So the solar system was formed from a gas enriched by previous generations of massive stars. And that's where all the planets come from. And therefore star formation is cyclical. They form, they evolve, they die. And they make more heavy elements that then go out into the interstellar medium. And what this does is it actually takes away some of the hydrogen in the galaxy. And so much of the hydrogen can be used up. If there's not a lot of hydrogen gas, then you can't have star formation. You need to have a big cloud of hydrogen gas. And eventually, that will all be used up, and there'll be just stars or just dust. And if you just have dust and just have stars, you can't form new stars. And we'll see in the galaxy section that there are certain types of galaxies, like ellipticals, that don't have any star formation going on. So they have very, very, very low metal type stars. Anyway, that's where stars come from. That's where so today what we're going to talk about are some historical supernovae that actually light up the skies today. In 1054, there was a guest star in the constellation of Taurus. It was seen by Chinese astronomers way, way back in 1054, and it was visible during the day for about a month and visible at night for almost 2 years. I think I got the wrong number here, 6 months. No, actually it's closer to 2 years. And this thing left behind the Crab Nebula, or Messier Object Number 1. And in 1572 and 1604, two supernovae occurred. The one in 1572 was written up extensively by Tycho Brahe. In 1604, Johannes Kepler wrote extensively about the supernova he observed. Now, they weren't the only people who did the observations. It's just they're the people who wrote the most about it, so we basically named the supernova after them. But there were numerous people who were watching the skies at that time, and they all saw this happen. So it wasn't just like some guy saw it. No, everyone on Earth saw it because they were bright enough. They were incredibly important supernovae, and they influenced astronomy and modern culture of their era. This is pretty important to remember how devastating these things could actually be for culture on Earth. And finally, we'll also talk about a supernova that happened between, say, 6,000 and 8,000 BC, the Vela supernova, and it was observed by the ancient Sumerians, and it appears in some of their ancient legends. So first, let's look at the Crab Nebula. The Crab Nebula is very, very prominent in the sky, and the Crab Nebula itself is something as by Messier object number 1, the first in Charles Messier's catalog of the 1700s. He actually went outside and looked at it and found this fuzzy patch in the sky and said, "Oh, that's not a comet, so I'll make it my list of things don't bother looking at because it's not a comet." However, back in July 4th of 1054, Chinese astronomers saw this new star in the sky, and it was much brighter than Venus, and it was visible during the day for about 2 years, and even it was seen by numerous cultures across the world. And if you look, we see this interesting petroglyph in Chaco Canyon, which is in the Four Corners region of New Mexico. And you can actually hike up and go see it. This area is, of course, kind of walled off because nobody wants to go mess with it. And there's a big old wasp nest up there. You can take that picture. I'm sure somebody will go knock that down because who wants wasps, right? Around you while you're trying to look at these pretty things. But you see there's a star-like image, a moon-like image, and a hand. And this is really interesting because the Anasazi actually gave us a map of where to look on that date for that new star. Because if you use a planetarium software such as Stellarium, you can actually go and go back in time to, say, July 4th, 1054, and you find just at the morning sky, the moon was right next to the Crab Nebula, and it was a crescent moon. And the crescent moon itself was right above the Crab Nebula, and the moon, and then the sun rose rather rapidly after this. Was in the morning sky, but then it's interesting is that the Anasazi had to have seen this arrangement in the sky because the next day the moon is 15 degrees away, and when it comes around again next month, it's actually in a completely different place in the sky. So they actually saw it on July 4th, 1054. They saw it in this position in the early sky, and the moon, when it gets back to this place in the sky, does not have the same phase, and it does not have the same location. And in fact, the sun and moon have slightly different positions, and makes it harder to see. So the Crab Nebula was visible, and the other thing that's interesting is look over there on the upper right, we see the head of Taurus the Bull with Aldebaran and the Hyades over there, which is that star cluster that we talked about extensively in previous lectures. But then if you carefully go back and look at the image from the Anasazi, you see this new star, you see the crescent moon, and you see the hand. Well, the hand has 5 fingers, and if you look at the V shape of Taurus with Aldebaran, those are 5 bright stars. So the V shape can be looked at as the 5 fingers. So we could think of them as the 5 fingers, the moon, and the star. And so the Anasazi were telling us that they saw this thing on that morning as the star rose. It was much, much, much brighter than anything else in the sky, and it was right next to the moon in the sky, and they could just see the fading glow of the Hyades in the sky along with it. And they found this to be so significant that they actually drew a picture of it and permanently drew the picture on the rocks so it could not be forgotten. And that's what they did back in July 5th. Of 1054, or July 4th, the morning of July 4th in 1054 AD. Well, that exploded back then, and here's some vital stats about Messier object number 1, the Crab Nebula. The mass of the progenitor star was about 9 times the mass of the Sun. The amount of ejecta inside the nebula that you see in the inset was about 2.5 times the mass of the Sun, which is an enormous amount of material. And there's a central neutron star, which we'll get to in the next set of lectures. And the central neutron star is about 1.4 times the mass of the Sun. The distance to the Crab Nebula is over 6,000 light years. So to have something so bright that it outshines Venus and can be visible during the day, 6,000 light years away, almost 6,500 light years away, meant it was extraordinarily bright in the sky. And if you go taking a peek at it, the angular size is about 5 arc minutes by about 7 arc minutes. And remember, there are 60 arc minutes in a degree, so it's actually a rather sizable nebula in a small telescope. I have hunted for it repeatedly, and I've always found it to be a very unsatisfying nebula. So you should get, if you want to go see it, you got to go see it, try to get it photographically, or what you want to try to do is use a very large aperture scope of at least 15 inches or greater in order to see it. The radius of it depends on which angle you're looking at. It's about 4 light years across one way and 6 light years across the long way. And the speed with which the material that you see in InSat is going is up to 1,500 kilometers per second. So that's really cooking by. The total luminosity is much, much, much greater than the Sun's at about 1.38 times 10 to the 34th watts. And the total amount of energy that's coming out in X-rays is just under 10% of that. Now, most of the luminosity, a significant fraction of the luminosity, comes out in radio light. And that's, in fact, this is a significant fraction of the total luminosity is in radio frequencies. What you're also looking at, the nebula itself, is permeated by a very strong magnetic field that is much, much stronger than the Earth's magnetic field. And the formation in order to create the nebula itself, or create the formation of this thing. What energy did it take in order to make the neutron star that's powering the appearance of the nebula? It cost an enormous amount of energy, much more energy than the Sun will put out in its entire lifetime. In fact, that's more energy than 1 billion stars will put out in 1 second. So there's this pulsar that's emitting radio pulses in the center that goes every 300ths of a second. So that's faster than you can snap your fingers. Something is blipping out there, and that blipping is slowing down by about 100,000th of a second per year. And that's called a pulsar. And we'll talk about pulsars and neutron stars next time, but I just wanted to show you that. So the Crab Nebula has many observational characteristics, and so we see the Hubble Space Telescope image taken with the Wide Field Planetary Camera 2, and this was taken by Hester at Arizona State University with the Hubble Space Telescope. And we see that the Hubble can see it's a narrow band filter set, and we can see that it looks like an astonishing wreck. And the changes are actually easily seen by going back and looking at the Crab Nebula over time. Now, why it's called the Crab Nebula, it's kind of weird. It doesn't look much like a crab to me. But when the Earl of Ross looked at this with his Leviathan telescope, which we'll talk about when we talk about the Great Debate of the 1900s, about the distance of the spiral nebulae, Earl of Ross looked at it, he sketched it, and he sketched a crab. I guess that's what he saw in a telescope visually. So, before photography, people made sketches, and that's his sketch was of a crab. So that's what he called it, and the name stuck because the crab. Why not? So we see other images on the either side. The upper left is X-ray emission at various frequencies. On the right is high-energy X-ray emission from the central region, and we see some bright dot with some disc-like structure and some sort of jet. We also see the superimposition of the X-ray image on the upper right, superimposed on the Hubble Space Telescope and in Spitzer Space Telescope image in the lower right. And we can see that the X-ray luminosity comes from a sizable portion of the image in the center. And then if you take an image and put a polarimeter inside it and look at sub-millimeter wavelength, which is much, 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 much longer than infrared, and that's what you get in the lower left. And you get a polarized image of it. And the polarimetry gives you the fact that there's a strong magnetic field. So let's look first at the polarized image. This was taken with a large apex bolometer camera at 870 microns. Remember that the typical wavelength of light is this is just under a millimeter in wavelength, but wavelengths of light are 10 to the minus 7th wavelengths, or 1,000 angstroms, or approximately 10 to the minus 7th meters, or a tenth of a micron. So this is about 1,000 times the wavelength of visible light, and that's the blue, red, and yellow that you see in this. But the lines indicate the polarization of the light. And so how you get the polarization is you put a polarizing filter, which we talked about in one of the earlier lectures. And a polarizing filter is basically a bunch of slats. And these slats go in front that only allow light whose electric field is vibrating in a particular direction to come through. And then you look at exactly where it is brightest, and that shows you the orientation of the polarization. And the Crab Nebula is strongly polarized, which indicates that it has a strong magnetic field, which is shaping the emitting electrons' orientations. So something is making it polarized. And this was given at a proceedings of the SPIE in September 12, 2012 with the introduction of this camera. Well, the explanation for all of the light that's coming from the Crab Nebula comes from synchrotron emission. So what is synchrotron emission? Well, if you take a very strong magnetic field and you accelerate electrons somehow up to nearly the speed of light, they will spiral around the magnetic field lines and travel along these helical paths at nearly the speed of light and spin and spin and spin. And as they go around in these helical paths, because they're accelerating, moving in a circle, but then that circle is getting dragged along upwards, as they're circling in the magnetic fields, that's an acceleration because a circular motion implies an acceleration towards the center of the circular motion. That means they will emit light, and they emit light in a specific way, and that specific way is given in the graph on the lower right. So a single electron is given in the upper right of the lower right of that thing, and it shows what the emission is like for a single electron. Now, if you have billions upon billions, or 10 to the 37th electrons, or 10 to the 50th electrons, something like that, spiraling around magnetic fields, you add up all those individual contributions, and the slopes on the things that go down to the right, they show you what the sum of all the contributions are, and it makes like a flat power law. It makes a yellow dashed line where you can say, oh, this is the power law emission of synchrotron radiation, which means that the nebula is not hot. It's not hot in the sense that we think of hot, because this is non-thermal emission. And non-thermal emission means it doesn't all have the same temperature. Now, if you had this gas that's going, really, really fast at nearly the speed of light, and it's mostly composed of electrons, you'd get hurt and it would give a sting, a burn. But when we think of things that are hot, we think of things that all are at the same temperature, and all have this, and that temperature characterizes the average motions of the randomness of the gas or solid that you think of. So on a hot day and a summer night, the air is hot because it has been warmed by the sun, so all the molecules in the atmosphere get warmed, and so as they get warm, they all move fast on average. But when you look at synchrotron emission, there's nothing for the electrons to bump into. So unlike the gas in the atmosphere when it gets on a hot day, the atoms and molecules in the Earth's atmosphere bump into each other and transfer energy until they all are moving roughly at the same average speed. Some are moving faster, some are moving slower, but the temperature can be roughly the same, and that's why we call how hot is it out. But the electrons in this magnetic field don't bump into each other. They simply spiral around the magnetic fields and emit light. And this emission of light is called synchrotron emission, radiation. And it's not thermal. It's not a thermal process because they're not bumping into each other. Now they're moving fast, but they're not bumping into each other and interacting to average out the speeds. And the electrons themselves are moving so incredibly fast. They're moving much faster than can be done in any particle collider on Earth by hundreds of times. So something's driving the energy of the electrons inside the Crab Nebula up to energies that are much greater than we can do in the Large Hadron Collider. And so here's another view of what we mean by that, of the electrons spiraling in a magnetic field, and as they do so, they emit light. And on the left-hand side, what we do is we see two types of emission, and see that bulby sort of thing that looks like an onion. Now, if the electron is moving slowly inside the magnetic field, it's accelerating towards the center in a circular orbit as it orbits inside a magnetic field. And if it's moving slowly, then the electron emits in all directions, and the light is not polarized. But if it's moving very, very, very fast, nearly the speed of light, then it actually gets narrowed and polarized into a beam, because that bulb now that's shooting out to the side, that's the shape of the emission of the electron as it spirals around. It doesn't take the emitting in all directions. In the electron's frame of reference, it is. But to an observer away from the electron, it does not. It looks like it's going in these beams. And that is an effect of general relativity, or special relativity more specifically. So as you spin an electron faster and faster and faster, it gets the light that it emits from synchrotron emission gets beamed and polarized. And it gets polarized along the edge of the circle that is being polarized along. So we can see that this is a bulb sort of shape, and it's also a flat, tall bulb. And the flat, tall bulb is the orientation of the polarization. So the Crab Nebula emits enormous amounts of X-rays, and these X-rays are also emitted through the synchrotron process, and we can see pretty easily inside this thing that there's these strange filaments and like bay-like structures and loops and curls, and what we're seeing here is something that's approximately a couple light years across, and right in the center is the thing that seems to be driving it. There is some sort of disk of material that seems to be spreading outwards from it, and there's like a jet sort of puffy thing coming out from the center, and that thing that's in the center is called a neutron star, or a pulsar, because it does pulse in a certain way, not in and out, but rotationally it pulses. There's a pulse associated with its rotation, but it's rotating very, very, very fast, about 33 times a second, and it's a very tiny object, and we're going to discuss what those kind of things are later. But the energy of this object and the density of this object and the provides all of the electromagnetic energy to fuel the electrons to spiral in the magnetic field such that they can spiral around in that noodly looking magnetic field structure and emit X-rays via synchrotron radiation. And if we look closely at this, we've now overlaid the X-ray image in purple on top of the Spitzer image, which is in red, and the yellow, which is the Hubble image. And remember, it's about 4 light years wide and about 6 light years long. So the X-ray image is emitted from an area that's about 2 light years across on either side. So that jet, that plumy jet in X-rays, is about a light year long. That's coming from the center, which is that bright dot in the center, and that is the pulsar neutron star that is causing all of this damage. And there's a close-up of it, and we can see that there's a bright dot. Don't worry about the bluish bright dot right above the central bright dot. That's a foreground star. But what we see is that there's a disk-like structure, and this has been shown to be moving and rotating, and we'll talk about more about that when we talk about neutron stars next time. So synchrotron radiation, though, is and the reason we think that this is the case is that the emission that's happening is so incredibly vast from these things that the X-ray emission would be so great that it would actually lose its energy, because it's spiraling on, it's emitting energy, so it doesn't do this forever. So it loses its speed as it's moving, and therefore spirals down, and so the electron then, instead of emitting X-rays after a few, like 5 or so years, it then slows down until it's emitting light only in radio frequencies. And when it's emitting in radio frequencies, it'll take about 1,000 years for it to slow down where it's not doing that either. So synchrotron radiation spans from X-ray to optical light to radio light. And that's why the Crab Nebula has incredible amounts of radio emission, because there's still a ton of electrons spinning around that are being replenished by this pulsar that's at the center. Now another bright supernova is the one that was observed in 1572. There were a couple of really important cultural things that happened around this time, and in between November 2 and 6 in 1572, there was a bright, bright, bright star in the northern sky in the constellation of Cassiopeia, and in fact you can see it in this image. I'm going to use my mouse to pass over the Cassiopeia. We see the W of Cassiopeia, and we see the bright star below it. Now Tycho Brahe made his name on this. He was really good at actually being a publicity hound, and he wrote extensively about this in his book De Nova de Nullis Aviae Memoria Prius Visa Stella, meaning the new star. And he published it 3 times, once in 1573, again in 1602, and finally a 3rd time in 1610. And it contains all his observations and the analysis of some other observers, including some of his competitors who he disrespected and threw some shade on, which was really kind of cool. But when it first emitted its light, it was brighter than Venus, and in fact, it was even used as the opening line in Act 1, Scene 1 of the play Hamlet. And so if you go take a look at it, remember the play Hamlet is actually called a disaster. Not just the tragedy of Hamlet, but is the disaster of Hamlet, meaning bad star. So disaster, meaning bad star, was actually part of the vernacular and part of the thinking of both the mythological and superstitious thinking, said that if you were born under a bad star, and you can even think of Romeo and Juliet as being star-crossed lovers. So with these disasters, and if you have a disaster, you would write about it, and that's what Shakespeare did. Funny enough, there is also references to Tycho Brahe's subsequent difficulties with the King of Denmark, because that's where he lived. And on the island of Uraniborg had some other names as well, such as it was pretty close to the island of Elsinore. And in fact, Tycho Brahe had 2 kinsmen. One of them was named Rosencrantz, and the other was named Guildenstern. So those 2 characters appear prominently in Hamlet as well. So there's a very strong link between this supernova, Tycho Brahe, and the play Hamlet by William Shakespeare. And this is the observation that Tycho Brahe did in 1572, and we can see the star marked by the letter I as being the new star, or Nova Stella in Latin. We see the W of Cassiopeia that he drew out in the stars G, C, D, E, and F that make out the W of Cassiopeia. And it was bright enough to be seen for a very, very long time. And we call this Supernova 1572A because it's the first supernova 1572 that's recorded. And on the lower right, what we're seeing is an X-ray image taken by the Chandra X-ray Observatory after it was launched by the Hubble space shuttle. And if we then go look in the infrared with the WISE observatory, which is the Wide Field Infrared Survey Explorer, Wide Field Infrared Survey Explorer by NASA Jet Propulsion Laboratory, Tycho Supernova shows up really bright in infrared as a spherical distribution. And that's because as the material from the supernova plows into the interstellar medium, it warms the gas and dust around it. And there's a bunch of gas and dust that you can see from the nebulosity that surrounds it. And it's heating that gas as the supernova material plows into it and warms it up enough to see. So Tycho Supernova also has some very interesting appearances. It's got this mottled sort of appearance, and it's brightly emitting in X-rays. And there's actually some different wavelengths of X-rays that are shown in these colors because of the different colors. The starry background is, of course, not X-rays. That is a digital sky survey that was just put as a background image just to show you what it looks like in the sky, if we could see it. But the foreground is the supernova remnant itself from 1572, and it was actually visible until about 1574. So it stayed visible in the sky for just about almost 2 years. Then in 1604, Johannes Kepler saw a star in the sky that was even brighter. And he wrote a bunch of things, and his book was called De Stella Nova in de Pedie Serpentari, which is the star in the Serpent Bearers, which is Ophiuchus, the Ophiuchus, the Serpent Bearer constellation. And those two stars that erupted forth in 1572 and 1604 assisted Galileo and Kepler and Brahe and many others in saying that Aristotle's ideas of the cosmos, that the heavens are unchanging and immutable, was wrong. And that was a philosophical change, because if the stars could change, then perhaps the Earth could move around the sun. And that was the big, big, big argument of the day. Does the Earth move around the sun? Copernicus said as much, but only published after his death. Galileo went into house arrest because he asserted that, and Kepler was just simply wandering around Europe trying to do the mathematics of it and trying to understand how it actually worked. Went over to Tycho Brahe, who Tycho Brahe himself didn't think that the Earth went around the sun, but he kind of made something modified. But Kepler eventually took the idea of the unchanging heavens being gone and replaced it with the Earth going around the sun, which then subsequently came back to Newton. Well, subsequent to that, the Hubble Space Telescope did a good observation of Kepler's supernova 1604A, and this is the view with the advanced camera for surveys that was done in August 2003, and we see the Hubble took a bunch of images in various narrow band filters that allowed it to look at specifically the light emitted by hydrogen, nitrogen, and oxygen, these specific things, and that's what you'd look for in a nebula such as this, because it won't be a thermal nebula, so you don't use a wide band filter. Use a very, very narrow band filter and look for bright emission. And hydrogen should be expected from a Type II supernova, which has exploded outer rim of a star, and nitrogen and oxygen should also be there, and that's what's seen. So the whiteness comes as a mix of hydrogen, nitrogen, and oxygen as it plows into the interstellar medium. The red is, of course, the hydrogen that we know from old, and then the rest is starlight in the background. And so the puffy, cloudy nature is the supernova remnant from that time. However, that's not the only view. The Chandra X-ray Observatory and the Spitzer Infrared Observatory also take a look at it, and it looks completely different in those views. In the blue is the Chandra X-ray high energy X-rays, and those things come because as the material from the supernova, which is traveling at thousands of kilometers per second, slams into the interstellar medium, it heats the interstellar medium and makes it glow in X-rays. And that's what that blue glow is on the outside. As the material shock heats the interstellar medium into glowing to X-rays. So basically, you've got some cloud of gas and of hydrogen gas sitting around going herp derp herp derp. Not what I'm going to do. I'm some molecules, and all of a sudden something comes along and hits you going 10,000 kilometers per second. You're going to be angry and emit some X-rays too. So behind that shock front is a cooler X-ray emitting gas. That is the thicker interior shell. That is the heated material that's behind the shock front that is occurring from the supernova. And finally, we see in the upper right of this image the optical image of Hubble Space Telescope, which actually traces the upper right area of the supernova remnant, as well as the Spitzer infrared image, which mirrors kind of the low energy X-rays. And that comes from the fact that we have the cooler interior material that is the slamming into as the interstellar medium itself. Some of the dust doesn't get as it cools, as it is also warmed by the X-rays, and as it's warmed by the X-rays, it glows in infrared. So that's some of the remnant dust that survived, that then glows that glows because of the brightness of the X-ray emitting material that's coming through it. So let's take a look close up of the three regions. There's one region in the upper right of the remnant. And we can see in X-rays it's glowing brightly, and in the visible light it's glowing brightly, and in the Spitzer infrared telescope area it's also glowing brightly. And that's because as the shock front interacts with the interstellar medium, and that's must be a place where there's a particularly large interstellar cloud. Now, we talked about the interstellar medium as having cloudy structures, and they might be dark clouds out there, and this is just the supernova remnant slamming into one of those dark clouds and heating it up until it glows in X-rays, and then those X-rays then illuminate some of the dust, and that dust glows in infrared. And those X-rays also then cool off some of the things and make the gas, the hydrogen gas that's inside of the inside of the gas cloud glow. So it illuminates this little poor hydrogen cloud of gas and dust that's now getting whacked and heated to X-ray emitting temperatures. Now what's funny is you can actually use this to actually determine the distance and the speeds. So what a number of researchers have done is actually have taken the Hubble Space Telescope, actually taken repeated images of the Hubble over periods of time and looked to see what's moved. And when you see what's moved, then you can determine how fast it's been moving, and that's how they determine the speed, the velocity speed, by taking subsequent images and differencing them, and you can see how fast it's moving. So the bright shocks are not moving as fast as the really faint shocks. So the faint shocks are the ones that are plowing out straight out from the star, but the brighter radiative shocks happen as those faint, really high-speed shocks keep moving along as they have gone through the cloud, and then the others just glow because, well, they've been kicked. But in the same sense that, imagine you have something going really fast, and it's a small, say, car, and you hit a big car with a small car, the big car is going to move a bit, but the small car is going to keep on moving if it's small enough, and the big car might just keep on going. But it's more like maybe you have 1,000 little cars and one big car, and sure, a few of them are going to hit the big car, and as a line of them go by, but the debris will heat up and make an explosion, and the other ones will keep going on by. So it'd be kind of like a grand chase across the desert with a line of cars. I don't even know what I'm talking about with that. But anyway, there's a shock wave that occurs because the gas from the explosion, the initial explosion, moving about 2,000 kilometers per second, that then slams and heats into and starts into motion the interstellar medium at about 100 kilometers per second. And it's found by just looking at the difference in brightness between the three filters of hydrogen, sulfur, and oxygen, that there is a significant overabundance of nitrogen in this supernova, which leads to understanding that it's a Type II supernova. And then we can look at, that's how it's also, the distance can be found. And here's how the distance is found. We take two consecutive images spaced almost 20 years apart, and you can see that the actual shock wave has changed with time. So the green is from 2003 and the red is from 1987. And actually a ground-based image, and then that 1987 image was compared against the Hubble 2003 image, and it showed a proper motion of about 1.5 arc seconds in about 16 years. When you know, and that is assuming a radial velocity perpendicular to the sun, assuming a radial velocity across the sky, that gives you that makes it like a base of a triangle, and that gives you the speed, first of all, of 1,600 kilometers per second. At a distance of over 12,000 light years. So you can actually determine the distance by the proper motion of these objects as they cruise across the sky. And it's Sankritanal that gave this particular one, that image right that we see here. Next we have the Cygnus loop, which is an amazing thing to go check out in a telescope. Many of the features that you see here, and yes, the loop itself is much larger than the full moon, so you can't actually see it, the whole thing, in an individual telescope. The Cygnus loop, which is an enormous shock front, is moving at about 300 kilometers per second, over 1 million miles an hour. It's over 5,000 years old. It's over about 100 light years across. And if we think what was happening about 5,000 years ago, that was when the first civilizations were appearing. And so this is in Cygnus, which is a northern hemisphere bright star. So over 5,000 years ago, the first empires were built, the first cities were being built, the first Greek civilizations were being built, and there was an eruption of civilization at the time, as this new star was gracing the skies above these people. And there's some beautiful pieces of elements of this thing, which is one of the wisps inside it called Pickering's or Fleming's wisp. And then there's the western veil, which sometimes is called the witch's broom, because the witch, which is that star, is riding the broom. And if we then look deeply with the Hubble Space Telescope into one of the elements of the witch's broom, we can definitely see that this looks like a shocked, heated region with these wispy things moving quickly across the sky. And as they move, this is visible light now, not X-ray light. But the visible light image, as the shock wave interacts with the interstellar medium, it heats it to X-ray degrees, and then that then cools off and glows in visible light. And you can definitely see that this is mixing with the interstellar medium, and this is the process by which the materials in the star go out into the interstellar medium, merge with it, become part of it, and then initiate and then start and then help to form more things, or actually seed new stars with the materials that could become planets. In this image alone, there's probably more hydrogen, more carbon and oxygen than there is in all the Earth, which is an astonishing thought to think that that's how much material is in just these wispy-looking clouds. Next, we can say how far the Cygnus loop is, because with the Hubble Space Telescope image from the Wide Field Planetary Camera 2 that we see in the back, this can be viewed over a couple of different observations by looking in that upper area where it's very, very thin, where you can actually see the shock wave move over time, and then looking at how fast the width of the line, the width of the emission line in the upper left, shows you how fast it's moving. So the spectrum width shows the speed that the shock is moving. And so now you know that it's moving 170 kilometers per second. And then what you do is you go back and see what the angular motion is across the sky over years, and that tells you how long it took to get from where it is to go to the center. And that shows you how big this thing is and how old it is. And again, that allows you to find the distance to it. Now, you can see in these two images that there's the Wide Field Planetary Camera image of distance of only a difference of only 4 years is able to actually discern a change in position of these wisps. And with that proper motion change of the wisps across the sky and the speed derived from the width of the bright line inside of that, we then see that the distance is about 1,800 light years. That would have been really close to have a supernova 1,800 light years away. It would have been extraordinarily bright in the sky 5,000 years ago. It would not have been missed at all by anyone. Why are there so many religiously based civilizations that appeared 5,000 years ago? Did somebody look up in the sky and say, "This was the most important thing. I know why this star is doing this. Follow me"? Is that possible? Maybe the stars in the sky help us to change human culture. If we then look at Cas A, which was came about in the middle of the 1600s, it was a 30 solar mass star that exploded, and it has X-ray emission as well, and it is powered by a neutron star. And we find from Hubble imagery that it is extremely bright, oxygen emission, so it has an extraordinarily oxygen-rich supernova remnant, as well as another supernova remnant, N94, which is, again, part of the Large Magellanic Cloud, and so it's very tough to see from the ground. In fact, you can't. So this is a really tricky one from Hubble Space Telescope data, and that's a very distant object in the Large Magellanic Cloud, about 1,600 light years away. Here's another supernova remnant that spans about 70 light years across, and it's only about 5,000 light years away, and it's between two very bright stars, Eta and Mu Geminorum, which are bright stars in the constellation of Gemini, and it's a rather big object. The size scale that we're looking at is that this thing is about 50 arc minutes across, which means that it's actually that bubble, that red bubbly shape, is actually twice the size of the moon in the sky. But it's hard to see in the sky without photographic telescopes. In fact, it is not possible to see without photography. And the reason it's bright in the upper left-hand area of the bubble is because it's slamming into that emission region in the upper left, behind the words in this image. And so as it slams into that hydrogen gas, it makes it glow, and it emits X-rays, and that then emits visible light in the form of hydrogen gas emission. There's another one, Supernova Remnant 132d, and possibly a supernova that will occur in our lifetimes, which is Eta Carina, which is in the southern hemisphere. But if it goes off, we'll definitely be able to notice that, but only people in the southern hemisphere, not northern hemisphere. And the Hubble Space Telescope has been looking at it. We see observational emissions of the thing shredding itself with ionized iron and nickel, argon and helium all throughout its spectrum. Now, All of these massive stars, these supernova massive stars, can be iron-rich supernova, and that's how we know that the oxygen is actually permeating the cosmos. By knowing their distances and their expansion rates, we can compare their relative sizes. Cas A is only about 350 years old. There's another one that's 2,000 years old, and N132d is about 3,000 years old. And all of these things are just expanding and expanding, and as they do so, they enrich the interstellar medium. And if you go out and look at other galaxies, such as M83, M83 is just creating supernovae like crazy. It's about 15 million light years away, and the smallest feature on the inset is about 72 light years. This is a barred spiral galaxy, has a starburst nucleus, and there's been 6 supernovae since 1923 that have been observed in it by astronomers. And there's huge numbers of core collapse stars in it, and at least 200 supernovas in less than 3,000 years have happened in this galaxy, only 15 million light years away. So if we zoom in on a particular thing, how do you look at this thing and determine what the supernova remnants are? Well, you look at their spectra. And the spectrum of an M83 supernova, we have 4 different lines that are actually highlighted by these different red items. And hydrogen emission is roughly the same between that and, say, an H2 region on the bottom. But a supernova remnant has oxygen emission. And so strong oxygen emission with strong hydrogen emission, and even strong sulfur emission, which is the blue line, S2, and O3 is the oxygen emission in green, that tells us that it's a supernova remnant as opposed to an emission nebula such as the Orion Nebula or something. So then you go and look for these circular sort of regions that are emitting a lot of oxygen, and this is what you find. You just go in front of these bulbs, and boom, 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 people are going and hunting and going and finding them and looking and looking and looking. And in fact, this group found 60 supernova remnants inside just that image that we were looking at before. So if you actually reduce that down, that image, and play with it, you can actually find these objects all throughout this other galaxy, and they're everywhere inside there. These supernova have been popping off all over the place. And if we then just look at the core region alone, you can see there's like 24 of them right in the core of the starburst core of that galaxy. But now I'm going to finish on one of the more interesting supernova remnants that possibly helped start civilization, or at least what we would call agriculture. And I'm going to make this assertion, and I know I'm wrong, but I'm just going to go with it. The Vela supernova remnant, about 11,000 years ago, in the southern constellation of Vela, there was a star that exploded. And when it did so 11,000 years ago, the outer layers of that star crashed into the interstellar medium, making the shockwave, and that's what that fluffy, shockwavy sort of puffy thing is in the center of this whole thing, by a Sky Factory, which was processed by David Martin. And so this image is also visible in X-rays, and this whole puffy, cloudy sort of, that's the wispy sort of webby thing that's in the middle. That's the nebula, that's the supernova remnant. The rest of it is H2 regions and star-forming regions, but the webbiness is from the exploding star that happened about 11,000 years ago. And there's a view of it in H-alpha taken by the Anglo-Australian Observatory. But the reason I bring this up is because Göbekli Tepe is an archaeological site found in southeastern Turkey. And it's known that this thing, now the actual age of the Vela supernova remnant is not well established. However, the tell is just the dig itself. And there are 2 phases of ritual use in this that date between roughly around 9,000 BC, and that's between 10 and the site was created. Lots of pillars were erected in a very regular structure, and each of these pillars in this regular structure has no administrative significance. It's on the top of a hill, and there's no living quarters amongst this thing. But this is the earliest part of the Neolithic period of human history. This one particular archaeological site from 9000 BC is the earliest human structures built in the world. And this marks the beginning of the Neolithic era of human history. And they put a bunch of stones on top of stones. And the German archaeological team dug there for almost 20 years under Klaus Schmidt. And Klaus Schmidt has an amazing TED Talk about this thing. And he tells about the efforts to uncover it and how important it is. And only weeks after he gave the TED Talk, he passed away. But through his incredible efforts, this archaeological treasure was unearthed in Turkey, and the Turkish government immediately gave him permission to do so, because if you find an amazing archaeological site in the home country of this and know that this is one of the most ancient sites in all of humanity, it's fascinating to think that this happened at about 9,000 years ago, or 9,000 BCE, which is about 11,000 years ago. The Vela supernova remnant is about 11,000 years old. Perhaps the stone structures that are in a circle that we see here are actually in arrangement to describe this cosmos. The circular arrangements, the oval shapes, are maybe in honor of all of the shapes of the stars in the sky. Now, many of the pillars in these structures, and they have these T-like structures, which are not seen in any other archaeological tell in the entire world. And when this died out, this culture in Göbekli Tepe died out only very soon after its foundation. Nothing like this happened again for approximately 4,000 years. And that's when the next supernova went off. It's interesting how this worked. And all of these stones have inscriptions of like animals that were familiar to the time. Well, what do we do when we look up in the sky? We see Taurus the bull, Aries the ram, Lyra the lyre. There's Cygnus the swan. We have the serpent bearer. We have the lady in the chair. We have and Scorpius and Cancer the crab. We name so many of the objects in the sky after animals on the ground or mythological beings. So it makes sense that if some great, great, great star appeared out of nowhere, you'd want to honor it. Or maybe somebody said, I know why that star is so important, and so convinced everybody to actually build these structures. Because in Klaus Schmidt's video, they actually tried to reconstruct exactly what it would take to build some of these things. And it takes hundreds of people just to put these stones on top of other stones using Neolithic technology, such as sand and ropes and wood and other stones. So this was a major undertaking that required major commitment and major enforcement of that commitment. Because most people at this time, they were agricultural. Or shepherds, and they went from hunter-gatherer societies to agricultural societies. But what exactly inspired these people to build this? Klaus Schmidt really doesn't know, but it's telling and very fascinating to think that we named the animals in the sky after animals we know. And all of these stones are set in circles, which are familiar from our studies of geocentric concepts about the cosmos. And the stones might very well be things that mark the constellations of that they know. But there's no necessary, but I'm sure that Klaus Schmidt would vociferously argue at this point, and there's nothing direct in the archaeological record, I'm sure, that deliberately says, oh, they're looking at a star in the sky. However, this occurred, and then 5,000 years later, another one occurred. And these stars, and when 1572 and 1604 came around, and those stars occurred, that changed much of human history. And so that we can also remember that the Reformation of the Catholic Church, or at least the Protestant Reformation by Martin Luther at the time, happened right around the time of the two supernovae. And this was the time when Martin Luther was saying that you don't need the hierarchy of the church in order to talk directly to God. So he hammered his note on the door right around the same time as these supernovae went off. So supernovae do a lot of things. If one were to go, and the last one that was seen naked eye was 1604 until 1987. That was the first one since 1604. So another one might go off at any time in our sky. There's no way to predict them. And when they do, It might cause a big change. It might cause somebody to, like, build a new religion. But at the very least, that star's explosion goes out into the cosmos, seeds the cosmos with more gas and more dust, enriched with iron, nitrogen, oxygen, and carbon, and all the elements of the periodic table, and those then merge to form other stars, which then make new planets. So we are looking at a wisp of gas, but that wisp of gas has more mass of carbon and oxygen in it than thousands upon thousands of Jupiters and Earths inside of that wispy-looking cloud. And that's what we really think about supernovae, that they are the beginnings of possibly even the solar system. The shockwave could have begun the solar system's collapse out of this cloud of gas and dust. And we know that these elements must have been created there, because that's the only place where they would be. All right, so next time we'll be talking about neutron stars, white dwarfs, and black holes. See you soon.